So, good afternoon and welcome to Dejan, or to wherever you are. In my case, to Paris at 6 a.m. This is the isogeny session 2.1 of PQCrypto 2021, and I'll be taking you through the next 45 minutes. The first talk in this session is Robbie Peterson, who'll be presenting Sairashi, distributed key generation for Seaside. So, Robbie, you can go ahead.
Okay, thank you very much. Can you see the slides?
Yep.
Okay. So thank you very much. First of all, also thanks to the chairs, and thank you for coming here, which I also can only describe as being 6 a.m. So I'm going to present Shirashi, which is a distributed key generation scheme for Seaside. This is joint work with Watt Brilliance, Lucas Disson, and Frédéric Packard. So what is Shirashi? So in our setting, it stands for a distributed key generation scheme that uses Shamir secret sharing, and that's based on very hard homogeneous spaces, which we will later instantiate with commutative supersingular isogenies, so in the Seaside setting. So, but Shirashi is also a Japanese dish, which can loosely be translated as a distributed sushi, so which is quite fitting in our setting. And basically, we base Shirashi on a concept we call very hard homogeneous spaces, which is a generalization of cyclic group where Diffie-Hellman type assumptions are hard. And this can then later be used to instantiate with isogenies, for example. And Shirashi also uses Shamir secret sharing, which is a way of distributing shares to a number of people so that any number above a certain threshold can reconstruct a secret. And usually this is done using polynomial interpolation. And then we introduce something new, which we call piecewise verifiable proofs, which is basically a means to generalize or translate Petersen commitments to very hard homogeneous spaces. And finally, we also need some zero knowledge proofs to make Shirashi actively secure. So I will focus this teaser more on these piecewise verifiable proofs because it's a new concept that we need for Shirashi. And more details can then be found in the full talk. So why do we need an alternative to Petersen commitments? Well, rather than introducing very hard homogeneous spaces from scratch, I will just try to give an intuition in relation to elliptic curve points. So elliptic curve points, for example, they form a group. And basically on this group, you can define a multiplication given by these square brackets, which is a multiplication map that allows us to apply a scalar to a point. And for example, if we say A times some point P, it's the same as adding a point P times with itself. In the very hard homogeneous spaces setting, we have a similar situation, and we also use a bracket notation to show similarities between the two. But instead of scalars acting on a group, we have scalars acting on a set. So in elliptic curve points, we can perform linear combinations. We even have pairings as a very powerful tool, and we can also associate multiplications. But in the very hard homogeneous spaces setting, since we're working with a set, we don't have any addition defined. We also have no pairings. So basically, the only thing we can do is we can see that consecutive actions of this bracket. So we call this a group action. So consecutive applications is the same as the sum of these two elements acting on some element E. But if we go to the hard problems, they again have a quite similar feel to them. So first of all, we have the inverting the group action is hard, which is similar to the D-log problem in elliptic curves, but also Diffie-Hellman types assumptions are assumed to be hard. Okay, so what are piecewise verifiable proofs? So the idea is to prove a relation where we have these few elements. So we have an E0 and E1, and then we have n elements xi. And basically we have a witness, which is a polynomial of degree k-1, f of x. And what this relation says is that E0 and E1 are connected by the group action through this witness, so through f evaluated at 0. And all these xi are just f, this polynomial evaluated at position I, so at 1 through n. And in the Shamir secret sharing, the idea is that we have n parties, and that each of these parties has a has a piece. So each of these parties knows the evaluation of the polynomial at exactly one position, and then no different position. And also they know E0 and E1, but they don't see the group action connecting them. And F0 is basically the shared secret between all these parties in this setting. So again, to make the case for the difference between elliptic curves and very homogeneous spaces, just assume this polynomial is given by some coefficients f, and also let P be generated of the point group. Then elliptic curve points, in the elliptic curve point setting, we can use Petersen commitments, which is basically just in this setting, we commit to the polynomial coefficients f, and then we get this different q, which are just polynomial coefficients applied to this group generator P. And then basically the verification is just to check if my share, so f of j for player j, applied to P is the same as some linear combination of this q. So I'm basically verifying if my share is correct in the exponent. And what's great about this is that every other player will use the same commitments and they will use the same formula. And so in the end, if everybody agrees, they will know they have a share of the same polynomial. So if you go back to very homogeneous spaces, this is just not possible. We can't have linear combinations, so we can't use anything related to the polynomial coefficients and combine them in any meaningful way, at least. So we came up with an alternative. So we went back to using the Sigma protocol. So basically the idea is we have this polynomial f, we evaluate it at positions 0 through n, and then we do a standard Sigma protocol commitment challenge response path. And so we generate another polynomial of degree k-1 and evaluate it at 0 through n, and then commit to it in some special way, which will be seen in more detail in the full talk. We use binary challenges, and then the response is simply another polynomial of degree k-1, which is b minus c times f. And so what players can do now is they can evaluate this polynomial at any position they want, and then they can verify if their share is correct using the evaluation at their position. So for example, player 1 verifies the polynomial at position 1 using this commitment and response, but also is able to verify at 0 because E0 and E1 are public parameters. Player 2 then does the same with position 2 and so on until player n did everything is until position n. So in the end, every player knows that their share is correct and that the share at 0 is correct and that both of them are combined by the same polynomial. And since all players use the same response, they will have the same result as in the Petersen commitment. So everybody will know that they have a share of polynomial of the correct degree, which interpolates to the same value. So they will know that the secret sharing is correct. And naively, this takes lambda n group actions operations, but we show in the paper and in the longer talk that we can actually reduce this to being only dependent on the security parameter lambda. And these are basically the steps with which we can then build Shirashi. So the first step is this Chamier secret sharing that I just explained. So we have these n parties, but every party basically performs this step. So basically every party generates a polynomial, sends shares to the other parties, and then wants to prove correctness of these shares. So I just show this here for player 1, but basically every player repeats the same process. So after receiving their shares, basically parties verify then if their share is correct using these PVPs I just explained. And then depending on, so if all shares are correct, everything is fine. But if shares are not correct, there are certain conditions under which players can be disqualified, which are also explained more in the longer talk. And basically at the end, after performing all these verifications, each player has n shares, but maybe players are disqualified, and basically the share they have is just the sum over all of the shares that the qualified players have. So everybody can just sum all of their correct shares together, and then they have a share of a polynomial, which at 0 is the shared secret key. So the shared secret key is also just defined by all of these polynomials evaluated at 0. And then the shared public key is then this just applied to some starting element E0. And then finally, the last step is we also have to compute this public key. So the idea here is we use a sequential structure, which is called a round robin. And basically, we have a starting element, and each player just applies their defined polynomial at 0 sequentially. And at every step, they will also use a zero-knowledge proof to prove that this action is correct. And then we will have the public key at the end of this. So that's it. So in conclusion, Shirashi becomes, because of these PVPs and zero-knowledge proofs, becomes robust and has active security. Robustness also follows some of the structure. And finally, we have a complexity which scales for the whole protocol, which scales with lambda n, so which is 18 seconds per player in CSide 512, which is quite long, but obviously we hope that we can improve this. And also, usually distributed key generation schemes have to be performed once, and then the keys can be used multiple times. That's it. Thank you for your attention.
Thank you, Robbie. If there are questions, we've got a few minutes for live questions, and questions can be posted to the Slack or to the chat, or you can try raising your hand. In the meantime, this is all like, you really need to know the structure of the class group for this?
Yes, that's correct.
Okay.
So, so we used CSide 512 because yes, we need to know the structure of the class group, and we also wrote this in the paper. Of course, this is a problem because CSide 512 is now not even NIST 1, has not even NIST 1 security level. But the thing is that class groups can be computed efficiently using quantum computers. So we kind of hope that if there's a quantum computer that can break CSide 512, it could potentially also be used to compute larger class groups. So that's kind of the silver lining.
Okay. But in the meantime, if you want to do timings for I guess larger groups, if you hope you can compute the class group, how do you expect these timings will change? I mean, it's in the security parameter, or it's in the size of the group?
So if the timings will change with respect to the security parameter or to the group size. Yeah. I mean, since both are usually related, it's in both. But yeah, definitely the group size will increase this these 18 seconds. So we used this. So there's this 40 milliseconds per isogeny estimate basically that we used. So we used a few optimizations in this, but this will definitely grow with the class group size. Yeah, I can't tell you by how much, but
okay, sure. And this is also depending a lot on the decision Diffie-Hellman in the homogeneous space.
Yes.
And I mean, I think we understand, you know, the analog of the discrete log and Diffie-Hellman relatively well in this world. What about DDH? Do you think this is? Do you anticipate like a gap here, or yeah? How confident are you in DDH in this setting? I guess
that's a difficult question.
It's a bit rough to put you on the spot with this, but
I'm sorry?
I'm saying it's a bit rough to put you on the spot with a question like this.
Yeah. I can also only just guess, but so far I don't think there's no real attempt at breaking DDH by itself. I think so. Yeah, I'm quite confident so far. I think if decisional Diffie-Hellman goes down, maybe it's not so far for everything else to go down with it. So I'm not really sure. Yeah. Can only guess here.
At least you'll be focusing attention on the problem, so people can work on it some more.
Yeah.
Yeah. Okay. So far, I haven't seen any other questions come through on the chat or on the Slack. But I guess you'll be following through the rest of the conference. So if people have questions that they want to post after the fact, then please go ahead and we can discuss this in the isogeny channel. Okay. So thank you very much.
Thank you.
We'll have a hopefully seamless transition onto the next talk. which will be Boris Wurtzer, will be telling us about SIMS, which is a simplification of SIGAMAL.
Can you see my screen?
Yep, that's perfect.
Okay, thanks. Hello, everyone. I am Boris from University of Romatre. I'm going to present SIMS, a simplification of SIGAMAL, a joint work with Christophe Petit. So in this work, what we do is we present a simple INCC attack on the variant of SIGAMAL suggested by Moria et al. At PQCrypto for INCCA security. Then we design a new INCCA PKE scheme that we call SIMS, which stands for simplification of SIGAMAL. SIMS is more efficient and provides more compact keys and ciphertext compared to SIGAMAL. So this short presentation we organize as follows. We first briefly describe C-site, yes, SIGAMAL, and then we present our construction SIMS. So C-site is nothing else than the classic Diffie-Hellman in the supersingular setting, where you work with supersingular curves defined over FP, and you replace the exponentiation by the class group action. And we also have here the discrete logarithm problem, the computational Diffie-Hellman problem, and the DDH problem. So with this key exchange, you can have the canonical LGAMAL encryption schemes that derives from it. And this LGAMAL scheme is not INCPA secure because the shared secret, which is a supersingular curve, can be easily distinguished from a random element, which here is usually an ordinary curve. So with this argument, the scheme is not INCPA secure, and one usually use a hash function to hash this shared secret before adding it to the plain text. So Moria et al., they try to ask themselves, can we really achieve this without using hash functions? And their answer was yes. They design SIGAMAL and CSIGAMAL, which are INCPA secure PKE schemes relying on C-site without using hash functions. So the idea of SIGAMAL is to let the curve the plane at the point on that shared secret curve. So usually have at the beginning a curve E0, and are you getting me? I get a message that my internet is everything okay?
Your sound's a little bit grainy, but otherwise it's mostly okay.
Okay, sorry. So at the beginning here, you have a starting curve E0 and a point of smooth order on E0. You apply an isogeny A to get a curve E1, P1. The public key is E1, P1, and the secret key is the isogeny. To encrypt a plain text M, Bob chooses a random isogeny B and applies this isogeny to E0, P0 to get the curve E3, P3. And he also applies this isogeny on E1, P1 to get a curve E4 and a point B, P1 that he scales with the plain text to obtain a point P4. The plain text is BE0, BP0, BA, the shared curve, and the point on the shared curve that is obtained by scaling the image of P0 with the plain text. So they notice that this ciphertext is a bit too large, and they try to suggest a variant CSIGAMAL, which have smaller ciphertext. The size of the ciphertext of CSIGAMAL are half that of SIGAMAL. We did not present CSIGAMAL in this short talk. We refer to the paper for an explicit presentation of CSIGAMAL. So what is the security level of, or what are the security that are provided? What are the different security type of securities that are provided by SIGAMAL? SIGAMAL is one-way PCA secure. It is also INCPA secure under a new assumption that the introduced, the point commutative supersingular decisional Diffie-Hellman, but it is not INCCA secure because the ciphertexts in fact are malleable. You can easily derive the ciphertext of 3m plus 1 when you are given the ciphertext of m. This is noticed in the paper, and in fact, they suggest that maybe one could remove the shared curve BAE0 from the ciphertext to obtain a scheme which is INCCA secure. So in our paper, we prove that a similar attack applies to this variant. So the variant also is not INCCA secure. All these attacks apply, in fact, because in the ciphertext, we have a curve, either the curve BE0 and a point BP0 on BE0, or the shared curve ABE0 and a point, let's say the plain text, scaled on the, and a point on this curve scaled by the plain text. So our idea is to either to remove the points for which, we have the base curve in the ciphertext, or to remove curves for which we have a point on them in the ciphertext. So what we do is, if we must have a curve in the ciphertext, we make sure we don't have a point on that curve in the ciphertext. And if we must have a point in the ciphertext, we make sure we don't have the base curve of that point in the ciphertext. So SIMS, the idea of SIMS is then to start back with the shared curve, with the starting curve E0, and the public key is AE0. To encrypt a plain text, Bob chooses a random ideal class B and apply this ideal class to E0 to obtain the public curve BE0. He does the same with E1 to obtain the shared curve E4, and he canonically generates a point PE4 on E4. This point generation is canonical, so anyone who gets the curve E4 can generate PE4 in polynomial time, and he scales PE4 with the plain text. To decrypt, Alice just recovers the shared curve E4 and generates the point PE4 and solve a discrete logarithm between P4 and PE4 to recover the plain text. So here, what is happening is that we are revealing a point on the shared curve, and the knowledge of this shared curve is, in fact, will make the knowledge of this shared curve by an adversary will make the scheme totally insecure. So we have to like blind this point that we are revealing, and what we do is we use a sort of randomizing function, which we call f of e, and our instantiation of the randomizing function is just a one-time path with the shared curve in such a way that the output is indistinguishable from a random element. And our ciphertext then are the curve BE3, which is BE0, and the image of this randomized, and the randomized version of the point P4. And this randomization is invertible. So Alice can always invert this randomization before she decrypts the ciphertext. So what are the advantages of SIMS compared to CGAMAL and CCGAMAL? SIMS is INCPA secure, relying only on the commutative supersingular DDH, which was not the case for CGAMAL because they were introducing a new assumption. SIMS is also INCCA secure, relying on a sort of knowledge of exponent type assumption. Here is the table summarizing the comparison between SIMS and CGAMAL and CCGAMAL. What we can notice from this table is that the private keys in CGAMAL and CCGAMAL are ideal classes, are integral ideal classes, while in SIMS, as in C side, they are ideal classes. So this is already one main advantage. And we also have the efficiency, the size of the keys and ciphertext. And moreover, we have the INCCA security. So thank you, and you can find more details either in the extended talk on YouTube or in the e-print version of the paper.
Okay, thank you, Boris. Once again, we can have questions in the chat or you can raise your hand, or even better in the Slack. Because if it's in the Slack, then the questions and the discussion will be there for people that can't be here at this particular point in time. So we've got a few minutes for questions. While we wait for anyone else's questions to come through. I've got one very naive question, where at the beginning of your talk you say, well, we can basically do a Seaside LGML without using hash functions. And my question is, what's so bad about using a hash function?
What's so bad about using a hash function?
Yeah.
I think the design is not what, this is my point of view. So I think the design is mostly about is not really about what's so bad about using hash function, but how can we do it if we did not have hash functions? I believe this was the main motivation of the authors of CGAML, which we then come to improve on the scheme. So I think it's just a novel construction. Not the aim is not efficiency, or I don't know, is like mathematical. We have this mathematician always like how can we do it if we don't have this tool? We have like a big set and we reduce some properties and we get a smaller set usually when you are in categories or something like that. So how you don't have hash function, how can you really design the INCPA secure PKE scheme? And I think in the past we usually have CCA secure PKE schemes that did not use hash functions, like the Schnorr construction and many others, I think.
Okay, just a quick follow-up on this. So Scott Fleur has asked in the Slack, he says that it sounds like the point is to avoid a hash function. And how doesn't I guess it's the coefficient AE act like a hash function? So better phrase, doesn't AE act like a hash function?
AEA?
AE, so A sub E.
The Montgomery coefficient of the shared curve.
Yeah.
I think we use it here to blind the point. What we do here is that the message is carried by a point instead of hashing the shared curve and doing the one-time part with the plain text. So the idea here is that if we let points carry the messages, then we don't need hash functions to get INCCA security. And I think one main importance of the construction is the fact that it may opens the way to different construction that maybe are very important. And I believe in the next future, maybe we'll see that the ideas that I use here may be used somewhere else to get advanced schemes that are. From my point of view, I find the CGAML construction interesting in the sense that you prove that you can obtain INCPA security without using hash function. But if you want to go to the implementation files or the practical use, I think this does not really have an importance. But in the design point of view, I believe, from my small point of view, that this may be nice for designing schemes. Yeah.
And hopefully we can, continue with that question in the Slack, I think, afterwards.
Okay, thank you very much. Thank you.
Just one very brief question. I can see that you're doing something very brave here by naming your protocol for something that is not obviously connected to the sea or pirates, but instead you're going for like classic 90s video games. Where did the name Sims come from?
I think it came from us, but we were motivated by the reviewers, the reviews we got from the reviewers, who said like the previous name of the scheme was not PC side. It was inside, and we were like saying intermediary super singular isogeny Diffie-Hellman. Then the reviewers said that this is not a Diffie-Hellman scheme. You should just try to rename it. Then while looking at the title, simplification of Sigamal, I said, oh, seems somewhere here, and that's it. So it did not really come from the video game, but just by coincidence, it's the name of the video game. Man.
Okay.
Yeah.
Great. Thanks a lot, Boris.
Thank you,
so
Ben.
yeah, please let's continue the hash function discussion in the Slack.
Thank you. Thank you.
And we'll transition to the next talk, which is Jorge Carabina, sorry. And if you're not an isogeny implementation specialist, then you might be surprised to be seeing a talk on discrete logarithms in PQCrypto. But this is actually a really critical step in compressed cyc, and so Jorge will be telling us about memory optimization techniques for computing discrete logarithms in compressed cyc.
Okay, thank you. Can you see my screen and hear me well?
Yep, that's perfect.
Okay, yeah, this is a joint work with Aaron and Giovandro, and I'll tell you about optimizing memory in cyc, in compressed cyc, more accurately. And we would like to thank all of the supporters of this research. Okay, first I'll talk about isogenies, very briefly describe cyc, and then move to compressed cyc, because our contributions are really focusing on the compressed cyc, which is a version of cyc where the public keys are compressed significantly. After defining the problem, I'll tell you about our contributions, which is really twofold, and then give you some implementation results. All right. So the P is a prime number, and FQ is a finite field of size P squared. We have our supersingular replicator defined over FQ, and this is P plus 1 square many FQ points. And then classical notation for the torsion group of replicators we denote by square brackets. So in particular, this replicator will have two torsion groups. One is 2 to the power E, the other is 3 to the power E, as we use in the protocol. Okay, for isogenies, given two elliptic curves, we denote isogenies by phi from E1 to E2. They define a group homomorphism, and their kernels are kernel of the isogeny phi. That's how we denote them. And the key observation is in cyc or similar protocols based on isogenies is given a kernel subgroup of a curve, you can construct a unique isogeny from that curve that you start with, and then you end up with on another curve up uniquely, which is unique up isomorphism. And if you choose your curve carefully, then given the kernel and the starting elliptic curve, you can compute this rather efficiently. And this is the famous picture of the computations in cyc-like protocols. The very left starting point is public parameters, a curve E, the generators of the torsion groups, PA, QA for the 2 to the power E torsion group, and PB, QB for 3 to the power E torsion group. Two parties are involved, Alice and Bob, A and B. So Alice has a secret key as A, as you see in the left upper corner of this picture. And then this allows Alice to pick a kernel subgroup and then compute the corresponding isogeny phi of A, and then ending up at another curve, E subscript A, together with some other image points of PB and QB under phi of A. And then B takes on from here, and similarly, B does something similar in the beginning, and then A takes over the public key of the user B, and they end up computing the same curve, which is, and then the J invariant of this curve becomes the source for their shared secret. Okay, so that's the basic version of the computational flow in this protocol. And if you look at the public keys of cyc, you really have the curve EA, which is specified by 2 points, 2 coefficients, and then 2 points on this curve. This linearly corresponds to 4 FQ elements or 8 log P bits equivalently. And then there's a nice sequence of research contributions where we can now compress this 8 log P bits into 3.5 log P bits. One sort of portion of this compression comes from the fact that you can replace those coefficients A and B by the chain variant of the curve. And also you can, instead of sending those points in their x coordinates, you can write them with respect to basis and then send the coefficients in this representation. So this has been known, but the bottleneck of this compression technique is that it doesn't come for free. You have to compute a pairing function, and on top of it, you have to solve the discrete logarithm problem of certain elements that you obtain from the pairing computations to a fixed space G. You do 4 of them, and fortunately enough, these group elements lie in a smooth order group where we can tackle the discrete logarithm problem relatively easily, but still takes some time. And the Poly-Hellman algorithm is the way to go in this case, the most efficient way. But more formally, we really try to tackle the discrete logarithm problem in a group of order L to the power E. So A is really small, 2 or 3 in psych, and E is really sort of large, from a couple of hundreds to more. And the key sort of technique to speed up those computations is to store a table of group elements, which you see here in this slide as T, indexed by 2 integers K and D. So K runs from 0 to E, D runs from 0 to L minus 1. So you have roughly E times L many group elements to store, and it's not trivial. And in the computation, we know in the Poly-Hellman, there are 2 critical steps to compute. One is a sequence of exponentiations by L. The other is a group multiplication. And then you repeat this process over some strategy. Just to show maybe more clearly, you start with a point H, that's the instance of the problem, and you compute a sequence of L exponentiations, which are those left traversals in the tree, and then you end up at the leaf of the tree, where you now solve the smaller discrete logarithm problem, or you do a table lookup, and then for each right traversal in the tree, you end up computing some group multiplications, and then you repeat this process. So the picture over here really corresponds to the classical Poly-Hellman algorithm, and then you can devise different strategies using the same tree, where you get more efficient algorithms to solve the same problem. But nevertheless, you have to really store this table T in both cases. So our contribution is to use the same compression, but now at least to compress the tables used in the Poly-Hellman algorithm a bit more. The first optimization, it comes in 2 really steps. The first step is very simple observation that instead of really looking at the exponents in those tables, we see it in those negative exponents in the representation. And when we do that, we use the fact that you can invert elements almost for free at the cost of negating. So like making pluses and negative signs, which is for free. So after you pair those elements with negative and positive exponents, you can discard all the negative exponents in your table, which is half of the elements. And when you need them, you can just negate the element that you need. So it comes really at a sort of very small and minor changes in the whole algorithm to do, when we list them over here. So the of course, the end result is nice because we can now reduce the tables by a factor of 2 immediately. The second optimization is more involved. We use torus-based representations of group elements in our scattering subgroups. So traditionally, we represent group elements in a subgroup of FQ by 2 FP elements using the vector space structure, but torus-based representations allow us to use only one single FP element. Theoretically, this gives us another factor 2 compression, but you have to watch out 2 things. One is like, how do my computations will change? And they change in a comparable manner. So if you look at the cost of group operations in traditional representations versus torus-based representations, they're really comparable. But one really challenge that we faced in this is the equality check of group elements. So in the torus-based representation, somehow you have to embed those elements into a projective space, which means one group element can have multiple representations, and it makes it really harder to run through those equality checks. And then you really have a lot of those representations which come at each leaf of your tree, and there are many of them. So after you have you do your overhead computations and the cost, then you really don't benefit from extra factor 2 compression. So we decided to replace those table lookups by solving the discrete logarithm problems one more time at each leaf. Where now you still work in a smaller subgroup of the secretomic group. So it's much smaller, but now we go through a direct method for looking for digit recoveries at each leaf. So that's our observation. And then to do this, we devise different algorithms to solve the discrete logarithm problems in a group of order L to the power omega, where we assume that we know the generator, which is rho in this representation. And then we devise two different types of algorithms. One class of algorithms which apply to any L and omega, but particularly efficient when L is 2 or 3. And they are linear in omega, which is which determines the order of the group. So these are algorithm 1 and 2 and 3 in the picture that you see over here in the table. And we also devise another algorithm which is exponential in omega, but it's somewhat useful, as we'll see in the next slide. So algorithm 2 is an optimized version of algorithm 1, and then algorithm 4 is just a different algorithm. And then algorithm 1 and 3 are the analogs of algorithm 1 and 2 for A is equal to 2. In the end, what we see is we can really benefit from both of those different classes of algorithms and combine them in an optimal way. So for simplicity, we take algorithm 2 and algorithm 4 and combine them to get to minimize the cost of the algorithm. And for n is equal to 3 case, we really are sticking to the algorithm 3 version. So there's really no hybrid of the algorithms when n is equal to 3. Okay, so in the end, we can benefit from this two sets of optimizations for n is equal to 2. So we can obtain a factor for compression of the tables using the Poly-Hellman algorithm when n is equal to 2, and we do not lose from the efficiency at all. And even we observe some very slight negligible speedups. When n is equal to 3, factor 2 compression comes with, again, like a full efficiency gain, but then factor 4 compression really loses in the efficiency, which is about like up to 9% in the overall protocol. So we decided to really have factor 4 compression for n is equal to 2, but then only use the factor 2 compression for n is equal to 3. So with the new versions of the algorithms, our table sizes have been updated. Once again, for n is equal to 2, with the same efficiency, we can cut the tables by a factor of 4 and cut the tables by a factor of 2 when n is equal to 3. And just for concrete sort of numbers, we list a number of operations, FP multiplications in this table. There are really two cases. Those first two examples are for n is equal to 2, and then the other two examples are for n is equal to 3. You could observe that the current versions of the current cost is really lower than the previous cost that have been deployed. And if table sizes are compressed by a factor of 4, and same is here, and when n is equal to 3, if tables are compressed almost by a factor of 4, but then you lose somewhat in the, it comes at the cost of like increasing the number of FP multiplications in the table, which doesn't happen if you choose to go with the factor 2 compression in n is equal to 3. So our results have been implemented in C, and they're available at the GitHub repo as I list over here. And we have more details in the paper. There's a full version of the paper in the ePrint with all the proofs of the theorems that we have. And also feel free to visit the pre-recorded video where we have more details. And always feel free to contact us. Thank you for listening to me.
So, thank you. We don't have much time left for, well, we've got almost no time left for questions, but once again, if there are questions about this talk or any of the other talks, please go ahead and post them in the Slack. That way we can continue discussing throughout the rest of the conference. I've just got one very, very rapid question. how do these costs compare to the cost of the pairing that you have to do before you apply these algorithms?
I don't have the number on top of my head, but overall the protocols, so we had about 25% to 40% loss in the discrete logarithm computation, which was consisting of about like 10 to 15% of the whole protocol. And which is, I think, maybe like pairings, I'm not sure about the percentage, but they should be really getting a good percentage of the sort of isogenies too. I don't have the numbers, but it's really sort of just like 40% times 50%. I will get like up to 9%. But
okay,
I'll have a look. I have to check.
Okay, great. Okay, thank you very much.
Thank you.
So we're now starting to eat into precious break time. So we'll wind up this session just now. I believe we come back in just under 14 minutes for a longer presentation, one of our invited talks. So I'd like to thank all of the speakers, our 3 speakers in this session again for really nice talks. And I invite everyone to continue our discussions in the Slack today and tomorrow. Okay, thank you.
screen. It isn't allowing me yet, but I appreciate the invitation to come and speak at PQCrypto. It would be great if we were all able to be there in South Korea together. Let's see, now I think I can share my screen. There we go. Okay, so hopefully you can see everything now.
It's okay.
Great. So on behalf of NIST, I will give a talk. As it was introduced, I'll talk about the history of our process, where we are now and where we are coming, or where we are headed to. We have the Olympics starting up pretty soon here, and there will be a lot of races. And I used to run, and the home stretch is that part right before the end where you're racing right before the finish line in front of the crowd. And that sort of feels like where we are in our third round of our process right now. So there's just a brief outline of the order of the talk that I'll be giving. I don't think I need to give much motivation as to why we're here. I think we're all very well aware that if we had a large-scale quantum computer, that Shor's algorithm would be able to break factoring and discrete logs, which would then destroy the crypto systems which we rely on for public key cryptography. At NIST, we have various cryptography standards in a variety of types: public key, symmetric key, hash functions, guidance. For post-quantum cryptography, we are most concerned with 3 of our standards that deal with public key cryptography. There's SP 856A and 56B, which deal with key establishment algorithms. And then we have FIPS 186, which includes digital signatures. And all of the algorithms in those standards would need to be replaced, which is why we're most focused on them. Quantum computers would have an impact on some of our other documents as well. Symmetric key algorithms such as block ciphers and hash functions would also be affected, but we can more easily deal with the effects. We can use a longer key, or we could use a longer output from the hash function. We don't have to completely swap out algorithms for that. So if we look back to how this process all started, NIST had put a project together to start looking at post-quantum, and one of our first concrete steps that we took was in April 2015 when we held the workshop. Of course, there was a lot of other work going on, a lot of other research going on. PQCrypto had been holding workshops for a while. But this was the first step that we had taken, and we held a workshop. I think it had about 100, 150 people from industry, academia, and government that came together at NIST to begin some of these discussions. And one of the questions we were asking was, is it time for us at NIST to begin taking steps towards standardization, or do we need more time to keep doing more research? And we didn't have an answer completely yet by the end of the workshop, but time kept moving. Not too long after the workshop, later on in the summer, the NSA, the National Security Agency, issued a bulletin that got a lot of people's attention. The National Security Agency doesn't often talk about cryptography, at least publicly. So when they do, people were noticing what they said. And part of what they said is they announced that they were beginning their transition to quantum-resistant algorithms in the not too distant future. And so people began to say, well, if the NSA is worried about this, maybe this is a serious threat that we need to start taking some action on. And so that just helped build momentum. And they also, the NSA also pointed to us at NIST and said, NIST will lead the way with standards. So a few more months passed, and in February of 2016, we published a short report on post-quantum cryptography. It was only something like 10 to 15 pages. It was just a pretty easy read that explained what post-quantum cryptography was, just kind of the basics, what some of the main families were, some of the main issues. And then it outlined our initial approach to what we would begin doing to start standardization. And this pretty much coincided with PQCrypto that was held in Fukuoka, Japan that same month in February of 2016. Many of you who are attending today were probably at that workshop. You can look for yourself in the picture and see if you can find yourself. And at that workshop, I gave a talk there where I announced that NIST would be beginning the process that we're involved in now, a worldwide competition-like process to select new public key algorithms to standardize. So here's a couple of the slides from that talk I gave. Basically, this call for proposals outlined what we were looking for. Specifically, we wanted to replace those standards that I'd mentioned at the beginning, SP 856A and B, which had key establishment, or equivalently public key encryption, and also our document FIPS 186, which had digital signatures. So we wanted to look for those first basic primitives. We know that there's other things that will need to be built on top of that, but we first have to start with the primitives. We saw our role in this as managing a process of achieving community consensus in a transparent and a timely manner. We didn't want to be the sole arbiters of everything. We definitely need the resources of the community and the input and the feedback that we get from everyone, but we knew that our role would be to manage this process. Right from the beginning, we said there would not be one winner. We were looking for different functionalities, looking for signatures, looking for encryption or key establishment. So there would need to be at least one algorithm for each of those. And we thought as well that it's likely we would need more than one algorithm for each of those functionalities. So we made it clear that there would be a small number, but there would be more than one algorithm that we thought would be standardized. We recognized that there was no, based on what we were seeing at the time, that there was no obvious solution that was just going to be the obvious drop-in replacement that would solve all our problems. While many of the algorithms have good advantages, they also seem to all have at least one disadvantage. So we hope that there would be several algorithms that would emerge as good choices and would get consensus from the community. We also put forth what we thought would be our timeline, and we said this would be subject to change, of course. But if you look at it, it's actually still pretty accurate. We've been able to stick to this timeline pretty well. So we announced that about a year and a half later, well, we announced that later that year we would have the detailed call for proposals that would include submission requirements and the evaluation criteria we would use to evaluate the algorithms. And then we gave submitters about a year from that time to prepare their algorithms to send in and submit to us. And then we thought it would take about 3 to 5 years of analysis before we had our first algorithms selected for standardization. And we're here, I think we're going to be finishing about the 4th year at the end of this 3rd round when we expect to announce algorithms. So somehow or other, we've been able to keep to this timeline. We said we'd have workshops, and we have done that, I think even more than what we anticipated. So the final requirements were published in a call for proposals that we put out, and we put it out for comment. We got some good feedback. We changed some of the things that we initially thought. For example, we'd initially requested some kind of key exchange algorithm. We thought perhaps more similar to the Diffie-Hellman algorithm, but it was recommended to us that we focus on chems instead. So we made that change. And then the deadline in November 2017, we weren't sure completely how many algorithms that we would get. I think for the AES, we'd had somewhere around 20 algorithms for that competition that we did. For SHA-3, we had around 64 algorithms. Well, no, I forget exactly how many we had for SHA-3. And then turned out we had 82 algorithms sent to us from around the world, including all 6 continents and a large number of countries. And if you look at the type of algorithms that were sent in, they followed mainly the established research lines that people were quite familiar with. Lattices and codes made up the bulk of the submissions. And then there was a number of multivariate schemes as well, a couple hash-based algorithms. All those were signatures. And then there were 13 algorithms that were kind of didn't fit any of those main families, were kind of a hodgepodge of other algorithms. So that's how we started this process. I won't go into all the requirements that we had in the call for proposal. This summarizes kind of the basic requirements that the submissions needed to have. They needed to be publicly disclosed and freely available during the process. We required all the submitters on the team to send in signed statements disclosing any patent info that they had on their algorithms. Submissions also had to include code. There had to be a reference and an optimized implementation. Those could be the same, but we want these algorithms to be implementable in a wide range of platforms. Had to provide at least one of signatures, public key encryption, or key establishment. And you needed to provide evidence for your security claims, including concrete values or parameters meeting our target security levels. So our security categories that we defined at the start, took us a while to come up with these. We had a lot of debate internally since it didn't seem there was a clear consensus as the best way to measure security for a lot of these algorithms. So we ended up deciding to tie it back to the amount of resources that it would take to break some of the symmetric key algorithms that we already had standardized at NIST. So for example, level 1 means that it would take as much resources to break your post-quantum algorithm as it would be to break AES, doing an exhaustive key search. And then we define the other levels in a similar fashion. Classically, like levels 1 and 2 are approximately the same, and 3 and 4 are, but a quantum computer would perhaps give you, would differentiate these security levels so that we would have 5 different levels. We asked submitters to focus on levels 1, 2, and 3. We thought that would provide enough security for the next several decades, but we know that there are also important applications that have needs for very high security, so we wanted to have level 5 as well. And we knew that this was going to be preliminary estimates when submitters sent these in, that it would be hard to kind of measure these resources. There's more than one way to kind of look at it, but it would at least begin, somehow we could begin to compare some of the apples and oranges that we would be receiving. So the first round began December 20th. It took us about 3 weeks once we got the submissions to kind of process them all, to read through them all, make sure they met all of our requirements, and then post them up on our webpage. It turns out 69 of the algorithms met all of our requirements. Pretty quickly, 5 of the algorithms were completely broken and the submitters withdrew them. So for most of the first round, we actually had 64 candidates that we were dealing with. The first round ended up being about 1 year in time. As I mentioned, there was a large geographical variance. We had submitters from around the world, and there was a total of 278 distinct submitters that were on the teams that submitted these algorithms. I think the highest, there was a couple submitters that had 7 algorithms, or I think even one submitter had 8 different algorithms. So there was a lot of work being done. Just a few months into the first round, we held a workshop. It was co-located with the 8th PQCrypto workshop in Fort Lauderdale, Florida. We had a good synergy there. I think we had about 350 people who were physically there attending. So we had a lot of good numbers and excitement there. That conference had a lot of presentations because we gave each of the 64 teams an opportunity to present on their algorithm. So if you remember that, that was a very kind of crazy with a huge number of talks of that workshop. We even had a tornado warning in the middle of it to make things exciting. So the first round had a lot of different things going on. There was a lot of cryptanalysis. There was probably about 15 to 20 of the 64 algorithms that were broken or had significant attacks just within the first few months. So I think people had a lot of fun at looking at those algorithms. There was a lot of research being published and presented in different workshops and journals. We created the PQC forum as a venue for discussion, and so there was a lot of questions being asked and so on there. We also had official comments as a way to kind of track comments for a particular algorithm, and we began to see preliminary benchmarking and so on. There were a lot of similar candidates, particularly in the lattice chems, that had a lot of the same kind of ideas being used. So we encouraged teams to merge. During that first round, we actually had 4 mergers, and each of those teams that merged made it into the second round. So in each case, it made a stronger algorithm. And at the end of the first round, we selected the 26 schemes that we thought were the most promising to move on into the second round. We had a lot of debate. There was a lot of good schemes that we had to leave behind because we needed to cut down the number to a smaller number so that we could focus on them. We mostly preserved the diversity of the type of algorithms that we had. So we preserved a lot of lattice and code-based algorithms, multivariate signatures, hash-based signatures, and so on and so forth. And we wrote a report that explained why we selected the 26 schemes that we did, and that was NIST 8240. So the second round, it ended up being about a year and a half. So it began right after the first round ended. And we had our workshop that was co-located with crypto. And we also had the PQCrypto workshop that year was in Chongqing, China, that I was able to give a talk at there as well. Cryptanalysis continued during the second round. So even though these schemes were viewed as promising, they survived the first round. All of these schemes, LAC, LeadDecrypt, Round 5, Rolo, RQC, LUOB, MQDSS, and QTesla, all had significant attacks or were even broken during the second round. So they did not advance on to the third round. The second round was delayed a little bit due to COVID, perhaps. We had, towards the end of the second round, we'd had some deadlines where we were requesting feedback, where we said, anything you want to tell us before we make our decision. And we ended up pushing that back for a little bit to give researchers more time. Reminds me, I guess in the first round, we also had a government shutdown that pushed back the end of the first round. So hopefully at the end of the third round, we don't have any similar sort of bad event happening. You can see the table there, the 26 algorithms, the different types that they were. And in the end, we selected the 15 algorithms to move on into the third round. We again issued a report. We talked about all 26 algorithms. We talked about why we either selected them or why we did not select them. And for the algorithms that were moving on into the third round, we tried to give some feedback or some things that we thought could be looked at, or that the submission teams might want to possibly change if we felt there was anything that needed that. So where are we now? We are more than, I'd say, halfway through the third round. We have 15 algorithms, and we categorize these into finalists and alternates. That's something we hadn't done before. And the reason we did that is we really wanted a small number of algorithms that we could focus on and that we could then get ready for standardization. On the other hand, we had a number of algorithms that we still thought were interesting and had a potential to be standardized. And so we had a hard time deciding what to do, but ultimately we decided that if we broke it down into 2 tracks, if we had finalists, then we could have people focus mostly on the finalists and get those ready during the third round so that they could be selected for standardization if we felt that they were ready for that. But then we would still continue to study the alternates and that they could potentially be standardized later. So that was kind of the reason that we did that. Any algorithm that we kept as an alternate, internally, we had many discussions to make sure that we did feel that there was a potential path for standardization for that algorithm. We didn't want to keep any algorithm around just because we thought it was interesting or would be cool research or anything like that. So as you can see, the finalists, we had 4 in the chems and encryption category. We had 5 alternates. And for digital signatures, we had 3 finalists and we had 3 alternates. And I can't get into too detailed as to all the different algorithms. I'll just give kind of a brief summary of the finalists and the alternates in this way here. So if we look at the lattice chems, there's 5 of them, and 3 of them are finalists, Kyber, Entru, and Saber, which are all based on structured lattices. Kyber and Saber are perhaps a little bit more similar based on module LWE or LWR, whereas Entru is based on a slightly different problem known as the Entru problem. If people hadn't seen, after our last workshop, our third NIST PQC standardization workshop, we encouraged Entru to add a category 5 parameter set, and they have now done that. So wanted to make sure people were aware of that. All 3 of these finalists, being structured lattices, they have good performance. And when I say that, I mean both in terms of efficiency, keygen, encapsulate, and decapsulate are all quite efficient. You get good performance numbers that way. And they all have good public key and ciphertext sizes. They're pretty balanced in that way. And so we thought that structured lattices were the most promising algorithms that could be used for the widest audiences, for the most applications at the end of the 3rd round. We expect to select at most one of these 3 algorithms for standardization, given that they are all based on structured lattices. And so we didn't feel that we need more than one of them. The 2 alternates, Entru Prime is also based on structured lattices. It made different design choices to protect against potential avenues of attack that the submitters felt that warranted it. It also has 2 different versions. It has kind of an Entru version as well as kind of a more LWE version. And then there's Photochem, which is not based on structured lattices. They took the kind of the security performance trade-off where they said, well, perhaps there might be some attack in the future based on the structure. And so we will remove the structure. And even though we're aware that that might cost a little bit in performance. So Photochem is a little bit slower, has bigger key sizes, ciphertext sizes, but seems to be a bit more conservative in terms of security. So we selected it as an alternate in case there were any approaches that were showing promise for attacking structured lattices. Or if you were more concerned about security and you could handle the performance hit, perhaps Photochem might be good for that kind of application. If we look at the other chems, there are 3 based on codes. Classic McLeese is the finalist. It's been around a long time. Everyone's pretty familiar with it. So we have pretty good confidence in the security that it's based on. The downside is of course, everyone's aware that Classic McLeese has very, very large public keys. However, its ciphertexts are also quite small. So for some applications, you may be able to manage having a large public key and take advantage of the small ciphertext. So it was selected as a finalist for that reason. There are 2 other chems based on codes. These are Bike and HQC. They introduce some structure to the codes as a way to get smaller key sizes. Similar to the structured lattices, they're pretty balanced in terms of their public key and ciphertext size and have pretty good all-around performance. There's still a few research issues that we think Bike and HQC need to work through, and so we selected them as alternates, anticipating that perhaps after a 4th round, one of these 2 algorithms could be ready for standardization and would provide a good complement to the one of our structured lattice-based chems that we end up selecting. And then finally, we have Psych. It's based on isogenies, the only submission based on isogenies. And it's very interesting, of course. I have a background in elliptic curves, so I like Psych a lot. It has the smallest key and ciphertext sizes, but as its trade-off there is it's a bit slower than a lot of the other candidates. So for some applications, that might work out okay, even though it's slower. Perhaps the The key sizes are what's most important to you. So we definitely think Cyc is a potential for being standardized later on. If we look at the signatures, we have two structured lattice-based signatures, dilithium and Falcon. Both of them have a slightly different design style, and both have good all-around performance, just like their kind of their chem counterparts. We expect to, again, select at most one for standardization, since they're both based on structured lattices. It's been suggested to us that we might want to consider standardizing more than one. That is something that we are taking a look at. Right now, I would say, I think we still expect to pick one, but we haven't completely ruled that out, I would say. Besides dilithium and Falcon, there's two that are based on kind of symmetric primitives. Picnic is based on zero knowledge proofs in a block cipher, very kind of interesting design. Had a lot of changes from round 1 to round 2 and into round 3. It's improved a lot. It's become more efficient. That's part of the reason we kept Picnic around, is we think it has great potential to continue improving into the 4th round. And then the other one would be Sphinx, which is based on hash-based signatures. Its security is very well understood. It's a very conservative scheme. And so it could provide, you know, if you need some quantum resistant signatures and need to really trust the security, it might be a good option for that. And there was two multivariate schemes. We had Rainbow and Gems. We thought Rainbow was a little bit better. Both of them have the profile that they have very large public keys, but have very small signatures. But as we have seen during the 3rd round, there was some cryptanalysis done. There were some papers that analyzed rank attacks dealing with multivariate that affected both Rainbow and Gems, and have called into question the security of them. The submitters have provided some feedback back. I'd say our team isn't completely convinced that we can trust them yet. So back in January of this year, we made a forum post outlining 2 steps that we might take as a result of this, what's going on with the signatures. Because if we flip back and look at how many signatures we have, if we have doubts about Rainbow and Gems, that puts us back down into the category of just having 4 signatures. 2 based on structured lattices, and then 2 that are based on symmetric primitives that are a little bit larger, a little bit slower. So we wanted to have more signature algorithms for this situation. So 2 potential steps that we outlined we could do. First, we mentioned that even though Sphinx was selected as an alternate, that we recognize it's a conservative choice in terms of its security. So at the end of the 3rd round, if we feel that we want to have a second signature algorithm, that Sphinx Plus could be considered for standardization. The feedback we received on that, most people seem to be in agreement or encouraging that would be all right with them. The second action item, we said that because we had a small number of signatures, we might want to introduce a way to have more signatures considered for standardization in the future. And so we got a little bit of feedback on that. Some of that suggested, well, you don't want it to interfere with the current process. So we took that into account. And I'll talk a little bit more about that. We have introduced a process, or we will introduce a process to allow for new signatures to be considered for standardization. So just a few weeks ago, we held our 3rd conference at NIST. It was a virtual workshop, and a lot of what I'm saying overlaps with what I said there, but being that this conference is being held in Asia, perhaps the time zones work out so that if you were in Asia, it was hard to listen to the NIST PQC conference, and now you're able to hear it now, so that might work out well. We had a lot of very good research papers and other applications that were discussed there. We had a lot of participants. There was over 400. We had a very active discussion on the Slack channels that we created there, a lot of good questions and comments. We provided all the 15 candidates in the third round the opportunity to provide an update on their algorithm to tell what any tweaks or changes that they made since the third round had begun, or any new research that they wanted to share. And all the video, the slides, and the papers are posted at our website. So if you missed that, you can go back and look at any of that. Two of the announcements we made, we'd mentioned before that we would likely do a fourth round, but we did confirm that we will for sure do a fourth round when the third round ends for some of the alternates that we want to continue to study. And we also announced that we would have kind of an on-ramp for considering new signature schemes. And talk more about that on another slide, give a little bit more of the details. And then just kind of in summary, these were some of the different topics that people presented on at the workshop. There's a lot about hardware and software implementations, side channels, both attacks and protection, cryptanalysis, in particular, the attack that broke gems was presented, and that was a really good paper. And then there was a lot of looking at how does PQC work on different applications and protocols, and will it fit? What kind of benchmarks are we seeing? Things like that. So what lies ahead? The third round, we're, as this talk says, we're kind of in the home stretch where pretty soon we at NIST will start deciding we'll begin our process to decide which algorithms that we will select. We anticipate that that will end at the end of this year, maybe the beginning of next year will be about the time the third round will end. And we will announce the finalist algorithms that we will standardize, and potentially Sphinx Plus, as our PQC forum post said. That's we consider that now kind of an option that we could select for standardization. And we want to emphasize kind of the algorithms that we're going to select at the end of the third round will include those that we feel will be able to be used by most applications. In particular, the structured lattice-based algorithms that we have, we feel that those will be very good for people to begin using as kind of general purpose chems and general purpose digital signature algorithms. We'll of course issue a report to explain why we made the selections that we did, and maybe why we didn't choose some of them. We'll also announce which algorithms will move on to the fourth round. The fourth round will be like the third round, where it'll be anywhere from a year to 18 months. And we're still interested in some of these algorithms to diversify our portfolio. We want to not put all our trust in structured lattices. If there happened to be some sort of advance or attack, and we needed to rely on a different security problem, we want to have other algorithms ready that would be standardized already that we could use as well. As well as some of these algorithms have different performance profiles, so some applications might want to use these other algorithms. There are algorithms that have large public key and small signatures or ciphertext. There's some signatures that have small public key and large signatures. So maybe these, and then there's Cyc that has very small key and ciphertext size. So some applications will want that. We expect that it will take us a little bit of time to write up the draft standard. We'll consult with the submission team. We'll put it out for public comment, and it will probably take us a year or two. So we expect that by 2024, the algorithms that we announced at the end of the third round, we'll have our first set of standards there. We anticipate having more standards. There will be algorithms in the fourth round that we will be looking at, and those could be standardized later. And then the on-ramp for signatures, that will continue on into the future, and those would potentially be standardized later. So even though we will have our first set of standards, and most likely those will be the kind of main algorithms, we believe that PQC standardization will continue on for years to come. Of course, we always revise the standards that we have as well. So this kind of gives us a time frame for when we can see the first ones. Okay, so talking a little bit about the on-ramp for signatures. We did not want it to interfere with our current process. So at the end of the third round, we will issue a new call for proposals. It'll probably be pretty similar to the original one that we issued, but it will be focused on just public key digital signature algorithms. And we'll reflect a little bit of what we've learned over the past 4 years. We'll also announce what the deadline for submission will be. It'll probably be 6 months to a year from when that call for proposals is issued. And we don't want to start kind of the whole process over. We're not looking to kind of get 80 new algorithms to consider. We want this to be much smaller in scope than our main effort that we have ongoing. We're hoping to just see if there's any new signature algorithms that we could add to our portfolio that would complement the signatures that we are still considering. And that's the main reason. We feel good about the structured lattice signatures that we have. We also still have some good options for either Sphinx Plus or Picnic, but it would be good to have another, in particular, a general purpose digital signature algorithm that would be able to be used by most applications that is not based on structured lattices. So that's the primary thing that we are hoping to target with this on-ramp for signatures. That isn't to say that's all that we want, though. We could be interested in other signature schemes that are targeted for certain applications. For example, a scheme that has very short signatures. So if you think you have an idea, you can submit it to us, or you could talk to us in advance and kind of get our feel for what we think that would be. Of course, since we're considering these for standardization, the more mature the scheme, the better. We only want to standardize algorithms that have had a lot of analysis publicly. That takes time and effort. And we're not promising that we will take every submission sent to us and put it out kind of like we did for the first round, where we took everything that was sent to us. We may decide to limit the number that from what we received to a smaller number to focus attention on just a small number. Okay, so how is NIST going to make its decisions here at the end of the third round? I'd say it's very similar to what we've done at the end of the first round and at the end of the second round. And these are not easy decisions. They're very difficult for us. Our team spends a lot of time talking and debating this. But we use the evaluation criteria that we set forth at the beginning of the process in the call for proposals. The first criteria is security. That's obviously the most important. We don't want to standardize anything that we are not confident in its security. We want to look at the number of security levels that are offered by its parameter sets. Want to look at, do we have confidence in a security proof? What are the known attacks? How expensive are they? How much resources do they take? What's the classical and quantum complexity? So we're looking for those kind of things. After security, performance. There's a large number of metrics. This includes things like how large are the key sizes, as well as how fast are the operations, how fast is signing, verifying, encapsulating decaps, and so forth. Are there decryption failures? What's the decryption failure rate? And there are some attacks that can take advantage of decryption failures, so we look closely at those issues. Then we look at benchmarks on different platforms, both in software and in hardware, to see, will these algorithms fit in the places that we want to use them in? Besides security and performance, there are a number of other issues, IP issues. I'm going to talk more about that on another slide. Side channel resistance is obviously very important. We're starting to see some good papers that are coming out in the third round dealing with protecting algorithms from side channel attacks. And then simplicity, flexibility, clarity of documentation, so on and so forth. We also take a look at everything else that we can find. We look at the tweaks that the submission teams made, as well as their explanations for those tweaks. We look at all the official comments in the PQC forum discussions. We look at those very closely. And as much as possible, we try to stay aware of all the research that's being done, that's being presented in workshops like PQCrypto or other crypto workshops, and in journals as well. So we try and take all that information and then we give detailed presentations internally on each algorithm. We ask as many questions as we need to. If we have questions, we go out and get the answers. And then we start trying to compare them to each other and make some decisions. And that's often the hardest part. So specifically, some of the questions that we know we're going to be focusing on. For the lattice cams, our main decision will be which of Kyber, Entru, and Sabre do we feel is the right one to standardize. And then similarly for the lattice signatures, the main decision is going to be between dilithium and Falcon. All the other algorithms will pretty much, to some degree, be their own distinct decision. I mean, some of them have some natural competitors. Bike and HQC are two code-based schemes, so in some sense they're competing. Sphinx Plus and Picnic have a similar performance profile in that they have small public keys and larger signatures and are based on symmetric primitives. So in some sense, they're kind of competing, because if we had one, we may not feel the need for the other. But then we have like Classic McLeese, we have Site that are kind of their own thing. And so the decision, do we want to standardize them, will be based kind of on their own. We want analysis to continue on all of the finalists. The third round is not over yet, and there are still very important questions that we have and research that we hope gets done to help us make our decision. But we do want people looking at Kyber, at Entru, at Sabre, at Classic McLeese, at Falcon, Dilithium, even still at Rainbow, even though it's had a pretty significant attack. Then I wanted to highlight one issue that we're seeing is turning out to be pretty important, and that's IP issues. In our original call for proposals, this is a quote, we said, NIST does not object in principle to algorithms or implementations which may require a patent claim where technical reasons justify this approach, but we will consider any factors which could hinder adoption in the evaluation process. So in our previous, our SHA-3 competition, it was a requirement that there could be no patents or IP on any of the algorithms. In consulting with our lawyers at NIST for the PQC process, our lawyers decided to change that, and that we would need to allow algorithms that could potentially have patents. So we had signed statements from the submitters where they would need to notify us of any patents that they had. Turns out those first party patents haven't been our primary concern so much. We know those patents, but it has been the case that there are some patents held by third parties that are turning out to be a little bit more thorny. And this is a very complicated area. None of us on the NIST PQC team are lawyers. Most of the researchers in the PQC field are not, lawyers. So it's hard to look at a potential patent and say, can we concretely say, does this apply or does it not apply? Because it's a legal issue. Nonetheless, we acknowledge the impact of encumbered technology on adoption. I think it's a widely held view that any crypto algorithm which has a patent is less likely to be adopted. And so we definitely want to consider that as a factor when we're deciding algorithms here in the third round. We're aware of a couple of third-party patents that may have, claims on some of the finalists and alternates that are still in our process. For the ones that we're aware of, we are actively engaging to try and resolve these IPR issues that we have. At our third workshop, we were able to link to some statements. There's a company called Isara that had some patents, and on their blog, they have a post there that explains their position. My summary of it is that their patents they'll release to be royalty free, but yeah, you want to read their statement so that you get it accurate. So because I can't speak for them. And then we also link to a statement from CNRS, which is a French agency which holds a couple of patents which potentially impact some of the lattice-based algorithms that are in our process. And CNRS, the direction that they're taking right now is, for some organizations, they feel that if an algorithm is selected that they feel infringes on their patent, that they would charge royalties on those organizations. So we are engaging in talks with CNRS. We are trying to resolve these issues, but we also want to acknowledge that we very well may not be able to resolve the IP concerns that we have and that the community has. When we have something concrete that we are able to share, we will share it. We are doing our best to work on this and resolve it. NIST does not have unlimited resources to try and address this. So in light of all this, we think the discussion that would be most helpful to us is not really about does this patent apply or not apply, but how should we factor in these issues into our process? If an algorithm has potential patent issues, whether or not it applies, whether we concretely know that or not, will that affect adoption? Will organizations implement that algorithm? What weight should NIST give that? We talked about this issue at our third workshop, and we asked for some public feedback, and we got a little bit. We would very much like to encourage public feedback on this topic. The more we get, we feel that is helpful to us in our discussions that we have. We recognize that not everyone will be able to speak publicly about this. Many companies will never speak publicly about any IP issues. So if you want to talk to us directly, you can do that as well, even if you're not able to speak publicly. Okay, so moving on, there are many research challenges that are still very interesting to be studied. Some of these, I'm sure, will not be, well, most of these will likely not be resolved before we have to make some of our standardization decisions, but they are important topics that we hope some of you can work on. So things like security proofs in ROM and QROM. For a lot of the lattice-based chems, they differed only in the ring they chose, or the module, or the field, or the noise distribution. And, they have their advantages, but is there any, do any of those really matter for security? Is there a best choice or a right choice? How to best measure security for lattice-based crypto? Concretely, how many bits? In the PQC forum over the past couple months, we had a lot of discussion in terms of, exactly how much security are some of our lattice algorithms providing. Yeah, I probably don't need to go through all these things. You can read them for yourself, but there's also specific algorithm questions. For example, Byte is working on getting an accurate decoding analysis so that they can claim CCA security. If not, they might just need to claim CPA security. So that's an example of an issue that pertains to Byte. And there are similar ones for other submissions. Likewise, yeah, some more topics that we still are happy to see analysis on. Like I said, there's been discussion on the PQC forum about the security of lattice-based candidates. Are they providing enough security to meet, say, level 1, category 1 or not? Is the effect of how much memory, does that change things? And we've engaged in those. Recently, just this week, in fact, there's been a little bit more discussion on the security of code-based candidates, and Ray wrote a post for us at NIST that I encourage you to read, and we asked for feedback on a couple of questions. I'm not going to go into details on them, but if this is of interest to you, or you're one of the code-based submission team members, we'd encourage you to provide feedback on the forum. So yeah, the transition to PQC will occur in the future. At the end of this year, when we select algorithms and begin to write the standards, that will signal, when we can start beginning the transition. But it's not too early to begin thinking about this transition, and we hope companies and organizations are aware that a transition is coming and doing what they can to prepare. We will issue more guidance on the transition, but that has to wait until we select the algorithms. We want to remind that you can do kind of a hybrid mode to combine shared secrets for key establishment And we included that in an update on one of our documents, SP 856C, where basically you can combine a NIST-approved algorithm and you concatenate it with any other shared secret derived from another algorithm, i.e. a PQC algorithm, and then you run it through a KDF and you can still get FIPS validation on that. The FIPS validation is only saying something about the NIST-approved algorithm, but nonetheless, if you use a PQC algorithm, you'd be providing some protection from quantum attacks. Kind of outside of our process, we also have a new standard that deals with stateful hash-based signature schemes. This follows some work done in the IETF, and we approve certain parameter sets for XMSS and LMS. These are not general purpose digital signature algorithms because the state has to be carefully managed, and if you do it wrong, then you completely lose security. So the documents there describe, where we feel these are appropriate. Mainly it's for applications like code signing, where you can carefully manage that state. And then I also want to highlight, in looking at issues related to the migration and transition, our NIST National Cybersecurity of Excellence is currently doing a lot of the work in this effort in conjunction with us, but they've issued a white paper and they have a project description that's pretty new that they're working jointly with the Department of Homeland Security to handle a lot of these topics. So I'd encourage you to look at their project and their white paper and their webpage. So in conclusion, we can start to see the light at the end of the tunnel, at least here for the third round. We know things will continue on after that, but it will be good to finally select some algorithms. It's been a long and complex process. NIST is very much grateful for all of your efforts. We could not do this on our own. We have a very good, strong team, but it's too small to have done all this work that you all are doing around the world. So we're grateful for that. Grateful for other standards organizations that are coordinating and communicating with us so that we have a unified effort in getting standards that will be able to be used worldwide and provide strong post-quantum algorithms. And then of course, we're always happy to answer any questions, communicate with anyone. You can find all our info on our webpage. And if you haven't signed up for the forum, that's where a lot of the discussion is going on. So I'd encourage you to sign up for that and participate in the discussion. And again, thank you for the invitation to talk, and I'll be happy to use the rest of the time to try and answer a few questions.
Okay. Thank you, Dustin, for your nice talk. So you can use the Slack channel, you can also use the chat to ask questions. Right now, in the chat, we have a comment by Dan Bernstein and Tanya Lange, which says that classic Machiavelli has smaller ciphertext than Psych. Maybe you want to comment on this?
Yeah, I think that's accurate. They're both pretty small, but I think they're right that classic Machiavelli is smaller in terms of ciphertext than Psych. If you look at the public key, Psych's got smaller public key by a wide margin, but yeah, I think they're correct.
Okay. Then we have a question on the Slack channel by Otto True, who asks, would the on-ramp be open to stateful schemes as well? For instance, XMSS could be. I understand that you talked about this earlier, but this new call for signatures could be also open to other stateful schemes?
I don't anticipate that it would be open to stateful schemes. We've already standardized 2 stateful schemes, including XMSS, in a different document. And since our primary target is signature algorithms, which are general purpose,
okay.
Stateful algorithms wouldn't really fit that as well. So I don't think so, no.
Okay, and so concerning this new call for signature schemes, what kind of algorithms do you expect here? Code-based, other ones? Do you have any idea here what you can expect?
Well, Yeah, there certainly could be code-based ones. There certainly maybe could be isogeny ones. That's a very active area of research. They're a little bit newer. We think it's very likely there could be some multivariate signature schemes. GEMS and Rainbow both had attacks, but there are other multivariate schemes, like just plain unbalanced oil and vinegar, for example, that could be submitted. Potentially other lattice-based schemes. I mean, we're hoping to get something different, but perhaps, you know, there could be some interesting lattice-based ones that have very small signatures if you're optimizing for that. So those would probably be the ones that are following kind of, that might have some maturity already. Of course, there could be other ideas that people have, and you're welcome to submit them to us.
Okay, and you mentioned for this new call that you might be very interested in having signatures, very small signatures, but do you have an idea what kind of public key would be acceptable here?
Good question. Well, we currently had Rainbow was a finalist, and it had small signatures. It had a pretty large public key, and that was something that we selected as a finalist. So something on that order might still be acceptable to us. We have Classic McLeese as a finalist, and it has a very large public key. So I don't have a hard upper bound, but I think we understand that if you're going to optimize to have a small signature, it's likely you're going to have a kind of a larger public key.
Okay. Let's see questions. And let me check with Slack. Okay, sorry. And so there are many questions now in the Slack channel. So there is one by Damien Stele, which talks about the CNRS patent claim. So he's concerned and puzzled actually by the vagueness of the CNRS patent claim. For instance, he says that it's potentially covering HQC and psych, even through CNRS signed IP statements. So more generally, did they make their claims and intention more precise since the far ground NIST workshop?
Well, in their discussions with us, they have some code-based patents. They have offered to release those for if we standardize a code-based algorithm. The ones that they feel potentially apply to lattice-based algorithms, they have named Kyber and Sabre as the two that they think that their patent covers. So I can't say, you know, whether it does or not, because I'm not qualified to state that, but those are the ones that they have told us about.
Okay, and now we also have a question by Tom Wiggers, which says that looking a bit more into the future, we'll need at some point go into post-quantum non-interactive key exchange versus CAMs, C-side, for instance.
Yeah, that's certainly a possibility. We wanted to first get just the basic primitives, but C-side does offer non-interactive key exchange, which would be useful. So that is a possibility. I can't say for certain right now if for sure that we would or that we wouldn't. But yeah, it's still up in the air at this point, but it could be.
Okay, and we have a question by Anton Tutoveanu. So would the number of existing implementation in different languages play a part in selection process? This is relevant to widespread adoption, of course.
Yeah, we are aware that if you standardize too many implementations or options or parameter sets, that it makes it hard for adoption. So there's a kind of a balancing act that you don't want to select too few, but you don't want to select too many. So we're going to have to try and find that balance. But yeah, we want to keep it as small as we can so that it's easier for adoption. It's hard to give any concrete answer on that.
Of course. we're pretty close actually to the end. So I guess Venist will answer the questions through the chat channel in the coming hours, I guess, or in the coming days. So
Sure.
this Slack channel will be open for this. And so thanks again, Dustin, for your talk and answers. And okay, let's move on to the next session in a few minutes. Thanks.
Thank you.
Hello everyone. Welcome to the industry track. My name is Kyung-Cheol Jung of National Security Research Institute of Korea. This session, there will be 5 talks on national strategy and adoption, industrial adoption, and 1 for quantum security. As a starting of this industrial track, I'm going to introduce Jin Bae-hong, Director General of the Ministry of Science and ICT, Korea, who is responsible for cybersecurity technology policy in Korea. He will give an opening message about the PQC transition policy in Korea. Let's welcome.
Good afternoon and good morning, distinguished guests, and ladies and gentlemen. I'm Jin Bae-hong, Director General of Cybersecurity and Network Policy Bureau at the Ministry of Science and ICT. Today, I am pleased to join prominent experts in the field of post-quantum cryptography from home and abroad. I would like to thank online participants of PQCrypto 2021 conference for joining us despite your busy schedule and sleeping time. I'm truly grateful to Professor Chun Jung-hee and staff for organizing this important gathering. Now we are preparing to enter the quantum computing era. As a result, there is a higher risk for new quantum computers breaking public key cryptography, which has been making our lives convenient and safe. Over the past 10 years, I know and understand many countries around the world have worked together for the transition to post-quantum cryptography. In the meantime, in Korea, many research institutes and companies, including Seoul National University, Korea University, and LGU Plus in Korea, had great achievements such as developing post-quantum cryptography algorithm and have piloted them on telecommunication network and ICT services. As part of the Digital New Deal initiative in Korea, we have worked with telecom operators in December 2020 to establish and operate dedicated lines deployed with post-quantum cryptography in factories and hospitals as a pilot project. With post-quantum cryptography deployed, factories transmitted and received production data, which is about 600 kilometers away from each other, then successfully apply the data to production facilities. Hospitals safely transmitted patient treatment data from hospital to data center in other districts. In addition, from early this year, 3 information security companies have carried out a pilot project to demonstrate post-quantum cryptography instead of the existing public key cryptography. In February this year, the Korean government established K-cybersecurity strategy as a comprehensive information security plan. In this plan, by 2025, $600 million will be invested to support the development of original technology for post-quantum cryptography, and to be piloted in the real-world services such as IoT devices and smart cities. I am aware that the United States and the European countries have established the strategy, the way forward for the transition to post-quantum cryptography, and have implemented the transition plan in stages. The Korean government is also planning to put post-quantum cryptography in place step by step after gathering feedback from ICT industries and experts in Korea. In the future, the government will spare no effort for the Korean research community and industry to deploy emerging technologies in order to ensure safety of the domestic ICT infrastructure. Furthermore, we will enhance international cooperation to promote cybersecurity and cryptographic technology to match international standards and jointly responsible to global threats. I would like to recognize the experts from domestic and international research institutes, universities, and business who attended the conference today for your commitments in developing cryptographic technology. I look forward to many more contributions from you in the coming years. Thank you.
Thank you. Next talk is PQC Transition ANSI View. ANSI is the French cybersecurity agency. Melissa Rossi will give the talk.
Hello, so I'm starting the screen share. So can you see my slides? Does it work? Guess it does. Okay, oops, sorry. So let's start. So I'm Melissa Rossi. I'm very glad to be here to present the post-quantum cryptographic transition in France and some ANSI's views. So I'm working at ANSI. So first, let's present what is ANSI. So we are a national cybersecurity authority role, and we focus on cybersecurity, and there is a special team that works on cryptography. So we have several roles. Exactly two for crypto. So we have an advisory role where we promote the use of state-of-the-art cryptographic standards. And for that, we publish some documents online. So we have, for example, national guidelines on crypto. And so we provide some advices on how to use a state-of-the-art cryptographic algorithms. So it's openly accessible online and it's in French. And we also have took part of the writing of European guidelines on crypto with a group of countries that's called SOGAIES. The goal of those guidelines is to have an harmonized cryptographic evaluation scheme. Inside of these countries. This document is called Agreed Cryptographic Mechanism, so it's in English and it's also openly accessible online. So this advisory role is not exactly the same as being a normalization agency. We do not define standards. We just put some advices on the existing cryptographic algorithms and how to use them. And beside this advisory role, we also have a regulatory role where we supervise the evaluation and delivery of security labels for cryptographic products. So in France, where if you're an industrial and you want to commercialize a security product, you can obtain a security visa. From ANSI. For example, CC certificates are one type of security visa. Maybe you know it. So CC is for a common criteria. So to get this visa in the French scheme, security evaluation comprise cryptographic evaluation tasks. So the evaluation labs will check if the product complies with the national guidelines and the European guidelines. And it also checks if there is no vulnerability before having this security visa. So these guidelines are evolve depending on the state-of-the-art advance. So let's talk about post-quantum cryptography. So in ANSI, we think that it's the most promising avenue towards the quantum threats and also to bring a diversity inside all the asymmetric primitives. So in France, there is a high academic and industrial interest in this topic. And we have many researchers that work on the design of algorithms or on the security analysis on the primitives, or even on cryptanalysis from the very theoretical one to the very concrete one on, for example, studying implementation security. So we have many academic labs and startups and companies that work on this topic. So we are following closely the NIST standardization process, and we think that it has a key role for the research because it acts as a catalyst. It helps having a strong involvement of the crypto research community, and it allows to focus on a restricted number of keys and signatures while preserving the biodiversity. So beyond this NIST objective to derive standards, what is important to us is that the past 3 rounds of standardization campaign provides a variety of algorithms and solid analysis, although it is recent. So it's very helpful for the research. So as was presented earlier, there will be a fourth round for extra analysis, and even it will be open to new signatures. So we think that it's a relevant idea given the progress on several domains. We were just we had slight concerns about the distinction finalist alternates. We were a little bit surprised to see that the structured lattices are almost all finalists, and Frodo, which is the only unstructured one, is in the alternate track. So it's for extra analysis or a longer standardization process. So as NIST stated, Frodo is a very conservative scheme. And so we think that it should be an option for developers who can afford this heavy scheme. So maybe it's a little bit too bad to separate it from the structured one, as both structured and unstructured schemes with lattices should be parallel option. Well, at least we think it like that. So let's first point out the fact that post-quantum cryptography, the maturity level of post-quantum algorithms should not be overestimated. It's approximately equivalent to the maturity level of RSA in the mid-19s. And so there is many immaturity facets. For example, the difficulty of the underlying problem in the classical and quantum computation models, the dimensioning, or how to integrate these schemes in protocols, or even the secure implementations. Those are not at the same state of research, but every thing in this list is still in a research process. So so this immaturity should not be overestimated, as I stated. And what's important is that the immaturity will not cease immediately after the publication of NIST standards. And so we need to acknowledge this and accept it, and we need to deal with it, and it should not serve as an argument for postponing the first deployments. So let's start with the initial recommendations for post-quantum transition in France. So first, we will not endorse any direct jump. So by direct jump, I mean drop-in replacements. So taking the pre-quantum and replacing it directly with the post-quantum algorithm. So this is not recommended for the short and medium term. There is one single exception for this, is the hash-based signatures. Because the underlying problem is trustworthy, but the range of their potential application is limited. So we advise to remedy this problem. We advise hybridation. So it's I'm sure you know it. So it's constructing a post-quantum mechanism over a recognized pre-quantum scheme. So in that way, we combine both security. So it works for chems and signatures. And so it allows to preserve the pre-quantum security and to add an extra protection against the quantum threats. It's interesting to know that there is a low performance penalty factor over a drop-in replacement. So this is a good idea for a start. Then what we advise is the sooner the better for the transition. For the security products that are aimed at offering long-lasting protection. So by long-lasting, we mean after 2030. Then ANSI encourages to start transitioning with a hybrid mechanism as soon as possible. And for all the security products, ANSI encourages crypto agility. So crypto agility means be flexible and be able to update the crypto algorithm with some flexibility by simple updates, well, as much as it's possible. We know that it's quite difficult, so depending on the product. So I will give more details about how we see the transition in ANSI. So we will give some, we will update our recommendations following 3 phases. We think that a gradual overlap transition is what's best for increasing trust. So that way it will be possible to better anticipate deployment problems while keeping the security, the high security. And there will be like a learning phase where it will be this learning phase will be beneficial before post-quantum crypto becomes mandatory. So we are today in what's called the phase 1, and this phase 1 will continue after the NIST, the first NIST standard are published. It will continue a little bit, and then we will go to phase 2, and then after phase 3. So I will explain each phase separately. So in phase 1, so it's today. It's already possible to ask for a security label for a product with a hybrid mechanism, so post-quantum and a recognized pre-quantum. So it's already included in the existing guidelines that were updated a few months ago. There is one important requirement, which is that we require no security regression. So by security regression, we mean that the scheme should be at least equivalent, the security should be at least equivalent to the security of the included pre-quantum scheme. So that way we do not have any security regression. And so the post-quantum security is considered more as an in-depth defense, so something like a bonus security. And since the NIST standardization process is ongoing and the schemes are evolving, we provide a relative freedom in the choice of the asymmetric post-quantum algorithm. We just require 2 things. First, we want a stable and well-studied specifications, for example, using NIST finalists or some trusted schemes in alternates. We also require conjectured post-quantum security level as high as possible for both the asymmetric primitives and the symmetric algorithms. So preferably NIST level 5. So this freedom allows to choose many post-quantum algorithms, and choosing algorithms selected by NIST for standardization is not an absolute prerequisite. Well, let's be realistic. We know that few exceptions will be expected in practice, at least for mainstream crypto. But one example could be that if a developer wants a very conservative security, we think that it will be possible to choose Frodocam, even if NIST decided not to standardize it soon. So this phase 1, as you can see, is more of a learning period where there is a flexibility on the choice of the asymmetric post-quantum algorithm, but it still encourages implementers to start early deployments. So phase 2 will be later, and it will straighten the security requirements, and we will ask for a post-quantum security assurance. So hybridation will be systematically applied, so it's mandatory, except for hash-based, as I said earlier. But then we will not consider post-quantum cryptography as an in-depth defense anymore. It will be more of an integral part of the security label. So for example, if a product gets a security label, there will be a mention saying, and it's post-quantum secure, so long-term secure. And to get this mention, there will be stronger requirements of the choice of the post-quantum primitives. So there will be an algorithm restriction where we will define the more restricting acceptability criteria for post-quantum algorithm in the security products. So this will be the work of our teams for defining which post-quantum algorithm are could be accepted and which not. We do not guarantee that the set of acceptable algorithm will exactly match the set of NIST standards. So yeah, for now it's not very defined. We will take some time to study all the possibilities. And then to encourage even more to transition to post-quantum security, ANSI will stop delivering labels for certain types of product if they claim long-term security and they do not offer post-quantum security. So that way it encourages to transition for more and more products. And after the transition will be finalized in this, the final phase, phase 3, where there are certain post-quantum skin could be optionally used without hybridation. And so post-quantum security will be mandatory for more and more types of products. And so we will be at the end of the transition. So for now, this was a little bit blurry because the timeline was not clear, and the examples there were no examples and acceptability criteria. But we will publish a white paper before the end of this year, detailing as much as we can this transition. Yes, and so as you can see, I just put the overlap transition here. The idea is really to keep the same assurance level while increasing post-quantum crypto assurance, and then optionally remove pre-quantum assurance. So this white paper will be available on ANSI's website, so before the end of this year. So stay tuned, and thank you for your attention. I'm happy to answer a question as much as I can.
Thank you. There's a little discussion on Slack channel. Scott Flowhlow said, hash-based signature has a limited range of application, you said. And Scott said, I believe you mean stateful HBS schemes. Sphinx Plus is a general signature scheme. And about this comment.
I think I understood the question. So maybe it's about the hash-based signatures. So actually, the simpler is to consider hash-based like stateful and not stateful, because the underlying problem, they provide proofs, and the underlying problem, the one-way security of hash function is trustworthy. If a hash-based signature is provided without hybridation in a security product, so to get the security label, we will need extra time to evaluate it. In theory, it's possible to get a security visa for a product with hash-based without hybridation, but then it will take extra time for making the analysis.
Thank you. Let's move to the next talk. The second talk is on activities on PQC and maybe QKD in Japan. Keita Sagawa of NTT will give the talk. Hello, we cannot hear your voice. Please check your sound. Keita, we cannot hear your voice.
Sorry, so yeah, the host
Okay.
disabled me to speak. Okay, thank you. Thank you for introduction. So let me share my screen. Gee. Can you see my slide?
Yes.
Okay, thank
Yes,
you. Okay, let's start my talk. So should. Okay, thank you for its introduction. So I'm Keita Kusagawa from NTT Social Informatics Laboratories from Japan. So today, I want to talk about activities on PQC in Japan. Let me start. So today, I want to talk about NIST PQC activities from Japan and PQC transition in CryptoRec. So CryptoRec is a public organization that recommends good ciphers for our Japanese government. And I finally talk a survey about other activities in Japan. So at first, I want to talk about the NIST PQC activities from Japan. So because this can be considered a benchmark of PQC research in Japan. As Dustin Moody presented in the previous section, so NIST has been standards PQC script ciphers. So they call for proposal in the end of 2016, and they received 82 submissions. And so round goes on. So now we are in round 3, and we have NIST select 4 finalists for encryption and 5 alternatives for encryption, and 3 finalists for signature and 3 alternative candidates for signatures. And they will select some ciphers from the candidates, and they also start round 4 in the next year. Okay. So today, I want to consider how are Japanese organizations involved in this standardization as a benchmark of PQC activities in Japan. Okay. So this is a round 1 candidates of NIST PQC standardization. So there are 69 encryption and signatures. So those from those of 69, I think 5 candidates involved in a Japanese organization. For example, so classic Mercury, so this is one of code-based encryption. So this cipher, the submitter of this cipher includes Tancho from Osaka University. And so there's another example for Ding key exchange. So this is proposed by Jintai Ding, and this is lattice-based encryption. And this submitters includes Tsuyoshi Takagi and Yuntao Wang from University of Tokyo and Kyushu University. And third one is Geophantos. So this is multivariate crypto systems. And so this submitters are all Japanese. So Akiyama Shimizu from Toshiba, and Goto from Hakodate University of Education, Okumura from Osaka University, and Takagi Ikematsu from Kyushu University, and Noita Hanaoka from ICE. The fourth one is Lotus. So this is a lattice-based encryption. And the submitters are from and Hayashi and Aono and Moriai from NICT. And so the final one is Rakos. So this is a code-based signature scheme. And the submitter includes Fukushima and Roy, Zu, Kiyomoto from KDDI, and Takagi from University at Tokyo. So as those examples shows, so many companies and universities commits NIST PQC standardization. But unfortunately, so there are some attacks on those schemes, and unfortunately, so in the round 2, so only classic materials survived. So, and meanwhile, so Tancho moved to Academia Sinica in the end of 2019. So there were no candidates involved in Japanese organization in round 2. And in round 3, so Saito and Kusagawa, so this is me, and Yamakawa from NTT joined to the N3 team. So now, so only N3 is only candidate involved in Japanese organization. But as I already said, so several researchers and engineers from Japanese company and universities commit to NIST PQC standardization. And so there's other activities like crypto analysis of NIST PQC candidates, also improvement algorithms, for example, so lattice-based lattice algorithms, and side channel and photo injection analysis against signature schemes and implementation of lattice signature schemes, and more functional and primitive protocols proposed by several researchers from Japan. So therefore, so this benchmark shows PQC research is very active in Japan. Okay. So next, so I want to talk about PQC in CryptoRec. Okay. So I'm wondering, so how CryptoRec is popular in the world. So therefore, so I at first introduce what is CryptoRec. So CryptoRec is a cryptography research and evaluation committees. And so this is a website for CryptoRec. And so this organization is established to evaluate and monitor the security of e-government recommended cipher. So this is so ciphers to use the e-government in Japan. And so they also so the purpose is also to examine the establishment of evaluation criteria for cryptographic modules. So according to this purposes, so the organization is like this form. So at the head advisory board for cryptographic technology, so they have board to advise recommend the ciphers to e-government. And they have also two committees, cryptographic technology evaluation committees and cryptographic technology promotion committee. And so the cryptographic technology evaluation committee monitors and evaluates the security and implementation property of cryptographic technology. And they also research on new generation cryptographic technology. And so they also have a cryptanalysis evaluation working group. And so I'm involved in this working group. Okay. So to recommend good ciphers for e-governments, so this CryptoRec maintains 3 lists for ciphers. The first one is the e-government recommended cipher list, and this includes DSA and Diffie-Hellman and AES, SHA-2 and HMAC and so on. So very standard cryptographic primitives. The second one is the candidate recommended ciphers list. So the list includes several candidates to be recommended ciphers. So therefore, so they include a MISTI 1 or SHA-3 and CHA-20 poly 35, like, and so on. They also have and CryptoRec also maintains a monitored cipher list. So this the ciphers in this list have some vulnerabilities or weakened, but they're still in the list because of forward interoperability. So the list includes a 3-key triple DES and SHA-1 and CBCMAC and so on. So CryptoRec inputs if the new cipher is proposed, so CryptoRec puts the ciphers to candidate list or recommended list. And then so if the cipher is vulnerable, so then the ciphers will go to the monitored list or deleted from the list. Like this, so CryptoRec maintains the recommended ciphers by using those lists. So this list is first published in 2003. And 2030, so they published a 3 lists, a recommended ciphers list and candidate list and monitored list. So this those lists are revised in 10 per 10 years. So therefore, so they will we Japanese people expect they will revise the list in 2023. Okay. So let us see so how this recommended list includes the good ciphers. Okay. So this is the e-government recommended ciphers list. So as you can see, so signature scheme includes the DSA, ECDSA, RCPSS, and so on. And encryption is RSOAP. And so they recommended Diffie-Hellman or ECD Diffie-Hellman as a key exchange. So, but all of them are not in PQC. So therefore, also CryptoRec studying PQC. So they published several reports on PQC in Japanese. So for example, so in 2050, so before the NIST starts PQC standardization, so they published a report on the LW, LPN, and approximation common beta problems. So, so they also actively studying PQC. For example, so 2019, so they report on they published a report on the PQC, and 2000 oh, sorry. So they also commissioned some researchers or company to report recent trends on PQC. So for example, so 2020, so Hosoyama, they commissioned Hosoyamada, researcher for on the symmetric key encryption scheme to report on the post-quantum security of symmetric key encryptions. Sorry. And the RepDAM report on the hybrid modes. And Takayasu report on implementation of Schwartz algorithm in the real quantum computers in this year. Sorry. So some researchers in the CryptoRex also experiment estimation of quantum computation. For example, the researchers in NICT and Keio University and other banks, they experiment on a discrete log problem on a real IBM Q machine. So according to the reports, so they can solve 2 to the Z is 1 modulo 3, but they fail to solve the discrete log problem on 2 to the Z is 2 modulo 3, or 4 to the Z is 2 modulo 7. So therefore, as those shows, so the discrete log problem is still hard on the real quantum machine. And so they also established a task force for post-quantum cryptography to how PQC how to handling the PQC in the REST. And so they published some reports in Japanese. So they gather 4 times, and so they discuss quantum computation and the post-quantum cryptography and how to handle the REST. So I'm not involved in this task force, but so as far as I understand, so they would start a working group on a guideline for PQC. And PQC may be not in the list, but in the guideline. So therefore, so CryptoRec will maintain the list, and additionally, so the guideline for PQC and PQCs. So this is the Japanese status of transition of PQC. Finally, so I review some other activities on transition, PQC transition. So for example, so the institute in Bank of Japan published some reports on PQC transitions. For example, so Kan and Une reports that recent trends on research and development of quantum computers. And Ito and Une and Seito wrote a report on the mitigation to PQCs. And the other Second, so this is a Japanese company, and they serve PKI in Japan. So they also implement some lattice-based signature in the hardware security module, and they compare performance of PQC in the real world. Okay, wrap up. This is the final one. And okay, so I introduced, so I reviewed Japanese activity on NIST PQC and some PQC transition by Japanese public sector crypto. And they may write a guideline for PQC, but they will not put PQC in their list. And so I also review other reports on the PQC transitions. Okay, thank you.
Thanks for the nice talk. Let's move to the third presentation. Next talk is on progress and challenges in the industrial adoption of PQC. Peter Purcell of Infineon will give the talk.
Do you see the presentation?
No.
Hello? I'm unmuted. Hello? Hello?
We can hear your voice, but we cannot see your slide.
Okay. What do you see?
Your face.
Okay. Screen two. No, it should be okay, I think. Do you see it now?
We can see.
Okay. Okay, thank you. So this talk is about progress and challenges in the industrial adoption of PQC. So I'd like to start with this picture. I think you might have seen something like this before, but it's very interesting from an industry viewpoint, because if we expect that universal quantum computers, powerful enough universal quantum computers, become available in 15 years, I know it's always 15 years, but whatever, plus minus couple of years doesn't matter all that much. Then we should start to act now, because in industry there are many devices and products where the lifetime is not measured in years, but sometimes even in decades. And so if we start to deploy these products now, then their lifetime might reach well into the age of the universal quantum computer. And this picture here even completely ignores the time to market, the time to adopt the new technology. It's if we start deploying it now. So what does this mean? This means that it is time to act now. The train is already moving and we have to get on it as long as we can. And for this reason, Infineon is, of course, actively pursuing an intensive research on post-quantum cryptography and all sorts of post-quantum cryptography, not just research development for our products, but we also pursue an academic effort. But I'm not here to make advertisement. Instead, I want to talk about some selected topics which are right at the border between academia and industry, and might be interesting here and as seen from an industry point of view. And now these topics are standardization, implementation, and the adaptation. And I'll start with standardization. So as you've seen in the last couple of talks, there are many different views on the future standardization, of post-quantum cryptography on many national and international levels, some of them more or less reliant on the NIST effort. So complementary to the NIST effort. And since this track is kind of like a tour around the world, I'm kind of the German representative, although I'm not German. But for this reason, I'd like to briefly talk about what the German BSI currently recommends. As a disclaimer, I'm not part of the BSI, so this is kind of an outsider view, more or less. So what the German BSI currently recommends, well, first of all, these generic recommendations that your product should have crypto agility so that you can adopt or switch to the new algorithms relatively soon as they are available, that you should increase the size of your symmetric keys, and that if you choose to go for PQC, then you should use some sort of hybrid protocol where you combine some classically crypto with post-quantum crypto. Now, the next recommendation is if you want to use PQC now, what you can do is use stateful hash-based signatures, XMSS and LMS, and their respective tree variants. Now, these stateful hash-based signature schemes come with quite some caveats, namely their number of signatures is limited beforehand. So you need to know how many messages you will sign at the time of key generation. And also the state management is non-trivial, let's say it like that. So there are problems with, for instance, fault attacks, what happens when you turn off the power before the state gets written back, or what happens if you want to back up a key. But these schemes are ready now. Their security is very well understood. And the one application that always comes up in context of these stateful hash-based signature schemes, as well as, which also mentioned by the BSI, is firmware updates, because this is one application where where it's possible to conceive a central signing party, and the central signing party keeps track of the state, and you don't have many messages to sign. You don't expect to push out thousands of firmware updates over the lifespan of a device. Now, the BSI also has an interesting stance on the more recent developments on the NIST candidates. Namely, they recommend two key encapsulation schemes to use as in part of a hybrid approaches, namely FrodoCam, based on unstructured lattices, and classic Mecha-leads on codes. So these are arguably the two most conservative choices when it comes to security. And the comment on the current finalist is that the level of trust on schemes using some sort of structured lattices is not as high yet. And also of note is that currently there are no more recent signatures recommended, like Falcon or Dilithium. This is because CAMs appear to be more of a pressing problem as of right now. But of course, this is just a snapshot, so this list will be extended in the future with NIST selected algorithms. Okay, now on to the next topic. The next topic is implementation, and it's more the topic that we at Infineon have to deal with. Now, of course, when it comes to implementations, we have seen a huge progress in implementation efficiency from all the published implementations. So it's quite some story. I started looking into PQC, I don't know, 5-6 years ago when I started my PhD back then, and I naively thought that, yeah, the implementation topic was pretty much solved. There's just breadcrumbs to pick up now. Yeah, I was wrong on that front. So there is still huge progress going on. We've seen progress on all sorts of platforms, from hardware to instruction set extensions to embedded microcontrollers and full-blown CPUs on vector units. And what's also interesting is that this progress actually comes from two sides. First, we've seen new implementation techniques but also the implementation efficiency also rose due to the newer schemes being arguably easier to implement. So they already have the implementation in mind, and they make it, for instance, a lot easier to implement them, at least in constant time, and sometimes even masked. So, one instance of that is that, for instance, that Gaussian samplers are not as present as they were a couple of years ago. All this led to the fact that runtime is now maybe less of a concern. I'm not saying not a concern, because in the embedded world it's never not a concern, but manageable, and the memory requirements are, yeah, doable, but yeah, might be a challenge. Now, what's also interesting is about implementation security, which is of course critically in the embedded world where Infineon is located, Infineon is found. And there as well, we've seen huge progress in attacks and countermeasures. You just need to have a look at the chess program, and you see lots of work done in both attacks and in their respective countermeasures. But here I have to say, yeah, okay, compared to the decades of work we had for RSA and ECC, I think we're still pretty much at the beginning, and there is lots of new stuff to be found. And here, I think it's also from experience. When I first naively thought that implementation was solved, it's now no one should think that the implementation security aspect is solved. And now to highlight this fact, I like to highlight some recent results from an academic viewpoint. First result is shameless self-promotion. So a colleague of mine and I published a paper describing one of the, if not the first fault attack on full-blown CCA secure lattice scams. And when you think about it, this was published in 2021, this year. The same year, we're planning to NIST will likely pick its first final choices. And the second paper that kind of caught my attention is a side-channel attack on masked Saber by Ngoedar. And what they do is they attack a masked implementation of Saber using just 16 traces, using an SPA kind of approach. Now their attack does not invalidate any security guarantees that the implementation gave, because their attack is technically a higher order. But still, this is quite interesting as an attacker, or if you're in industry and evaluation lab, well, it will go the way of least resistance, meaning that if the implementation is masked, well, it doesn't help if there is a way around this masking. And now my personal opinion is that there will be likely many more possible attack venues. For instance, faults just getting started. There will be, I think, a lot more attacks in using algebraic techniques or side-channel assisted chosen ciphertext attacks, which is the category that the paper on the right falls into. Now, what we can't do is now wait for us to find out what possible implementation techniques there are possible. So we have to prepare the implementations now. So what we have to do is consider implementation and sets of countermeasures that can protect us against all sorts of implementation techniques, all sorts of implementation attacks. And there we also have to anticipate future attacks while developing this countermeasure. So we can't just say, okay, this is the state of the art now. We have to think ahead what might come, and we have to incorporate these faults into the countermeasures. Okay, so the final topic I'll briefly touch is adaptation. So there's just one topic that I'd like to talk about, and this is, of course, this is PQC on a protocol or application level, because, well, the NIST effort is solely focuses solely on the primitives, on signatures and chems. But of course, you want to use these schemes in some protocol, which get then embedded into an application. And our one question one has to ask is, are these schemes really a drop-in replacement of existing primitives? Is it possible to use them as a drop-in replacement? Sometimes yes, or often yes, sometimes not, if you need some Diffie-Hellman property, for instance, which the current finalists don't really offer. And the next topic is also, is it ideal to use them as a drop-in replacement? Because sometimes it might make sense to replace, for instance, signature via a chem if it's possible, because the current finalists have some problems. First of all, they are slower than chems. If you have a look at the numbers of PQM4, which runs on an ARM device, the Falcon, we don't know much about, there is not much published work on the side channel resistance of Falcon. And with the lithium, there's the problem that the runtime is non-deterministic. And that's, of course, a problem in real-time applications if you have any sort of user interaction. And it turns out you can sometimes replace signatures with chems. So there was this ChemTLS work, which got some publicity. But we also tried to evaluate something like this. We implemented a post-quantum key exchange protocol on an automotive microcontroller of ours. So this key exchange protocol is based on a general AIC that's free-pass authenticated key exchange, doesn't need signatures except on the certificates, on the public keys, and offers forward secrecy. And we use XMSS as signatures for the certificates. What's interesting, what's maybe worth a little talking about is internally, this AIC generates an ephemeral key, and it might make sense to use just a CPU or secure primitive inside of this AIC instead of CCA. Might save a little some resources. So this brings me to the end. So just a short conclusion: the preparation for the transition is in full swing. Some challenges remain. For instance, there might be novel side channel attacks, and the adaptation of protocols is also in the works, and plus there is standardization. So it's an effort from many sides, academia and industry, but we're on it. Thank you.
Thank you for the nice talk. Let's move to the next talk. Next talk is on introduction of PQC pilot infrastructures and services in the industrial area. Kyung-hak Moon of LG U+ will give the talk.
Good afternoon. My name is Kyung-hak Moon from LG U+, which is Korean internet service provider. Now I'm going to present the introduction of a PQC pilot infrastructure and services in the industrial area. This is my contents. I'm talking in this order. Yeah. As we all know, the advent of quantum computer threatens modern crypto systems. In particular, public key crypto system will be broken. And Google says that they build a broadly usable quantum computer by 2029, and IBM is installing its first commercial quantum computer at 2021. This threat is not a matter of the future, especially ISP is directly facing it. There are two approaches for achieving quantum security, QKD and PQC. QKD is quantum key distribution technique by using unduplicable quantum keys. The quantum property is achieved by single photon generation. This figure shows the fundamental of QKD system, and QKD system requires the separable the quantum channel for this. And this is a physical technique, so it has some restriction for its quantum property, and such as the limitation of transmission length and the limitation of delivery medium. On the other hand, PQC achieves quantum security by using unsolvable mathematical problems by quantum computer. In this case, a single physical channel can be used to provide cryptographic service. In main features of PQC are like that. Its key exchange is using unsolvable problem by quantum computer, and it has variable applicability in the form of software, and it can deliver its key through various media such as optical fiber and the air, and also coaxial cables. And it can upgrading the modern crypto system to quantum security without any physical equipment. LG U+ has been developing PQC-based service as a proactive response to quantum security since 2018. In 2018, we developed the world's first PQC applied optical transmission equipment. Since 2019, we have been developing various pilot services that apply PQC. Also, we pay attention to authentication, so we are developing a physical unclonable function for enhanced authentication in cooperation with ICTK. And PUP has a function of secure protection of its certificate private key, and it is applicable to smartphone and IoT devices authentication. It can be made as USB type of security token and PUP USIM and IC card. We intended to apply quantum security to expanding on-tech service by combining this PQC and enhanced authentication technology. In this chapter, I will talk about the advantage of PQC from the ISP's point of view, the reason we choose PQC, and please note that the advantages are in aspect of transmission network adoption. PQC is applicable to various network topology. This is because PQC has capability to relaying and switching its key via network nodes. It works on the header of data frames. when constructing a PQC transmission network with a simple ring structure, you only need to place PQC transmission equipment at each handle point. This is same to mesh and other structures, so PQC transmission equipment are only needed to place at the each endpoint. So it has capability to respond to various network environment, and it can be spreading to various industry. And then PQC is capable of encrypted transmission over long distance. Strictly speaking, there is no communication distance limitation according to encryption. The average distance between industrial complex in South Korea is 249 kilometers. The longest distance is more than 500 kilometers, and even it crosses the sea. So its cryptographic transmission system requires a stable key exchange network that allows the use of submarine cable. And the PQC can carry with quantum security over them. The PQC is applicable to various network services. PQC algorithm can be applied to various network layer 1 and 2 and 3, and so on and so forth. And media channel, and it can be transmitted from through various media channel such as wire and wireless. It is rare for data is passed through only one type of network and one type of medium until it's transmitted. This is an example of a home office service. In office network, the local network composed of UTP, which is copper, and backbone network is composed of L3 switch, and the line maybe is optical fiber. And there are also wireless networks such as Wi-Fi. And then when connecting from mobile, it goes through wireless access. It's 5G and more complex networks. Any network connection can be security weak point. And PQC can be a good solution because it can be applied in various ways. The advantage of PQC explained so far may not be special because it is software-based. However, for that reason, it is an important advantage that the ISP must be keeping and providing to our customers. In this chapter, I will introduce PQC transmission equipment and pilot services. This is our PQC optical transmission equipment. This is our OIDM. This equipment is specialized for long-distance transmission of large capacity data. In general, the typical transmission distance is over several thousand kilometers, and capacity is several terabps. And this is core model of PQC transmission. PQC transponder. It provides 4 ports of 10G encryption service, and it provides a layer 1 quantum security. And this is our Lizard, the domestic DTS standard PQC key exchange algorithm is built in. This is invented by Professor Jung Chun Labs in Seoul National University. It also has QRNG for secure key generation, and it has low encryption latency. Nowadays many internet services require very low latency for real-time service. This is PQC transmission network development example. Transmission network consists of separated several link network. Recently, it transforms to a kind of mesh network. Any variable is topology. There are many nodes which the networks are connected to. This point may become security weak point. Our quantum security is provided by configuring both endpoint without additional transmission line and relay node in existing transmission network. And there is no distance restriction by encryption. And it can provide the protection switching of encrypted signal for its survivable. These are cases of PQC transmission systems, and this was done as a Korean New Deal project. The equipment previously talked was applied. And protection was also provided for service survivability. And communication and encryption functions are controlled by a management server. And these services were verified by domestic TTA testing. Two pilot PQC network were deployed. First is an industry, LG Innotek. It is electronic model manufacturer famous of camera model. PQC private line services was deployed between database server, which is in Pyeongtaek, and is connected to Busan database. The transmission capacity was 10 Gbps, and its distance was 606 kilometers. And it also provides service protection functions. PQC medical reference was similar. It was provided to Ulji Medical Center in Korea, the database which has restricted patient data. This data is communicated to Seoul Center from Daejeon. The distance is over 200 kilometers and capacity is also 10 Gbps. Also, we have reference for PQC application. These are cases of PQC application, and we applied PQC to the TLS protocol to provide quantum security at the application layer. Specifically, the key exchange stack inside the TLS protocol was replaced with OR Lizard, which is a PQC key exchange algorithm. PQC TLS is used for secure session connection between the server and then manage the industrial confidential data and the application service that access it. Also, physical unclonable function, POP chip based authentication token is applied for qualified user. These two technique-based data transmission app is deployed to LG Innotek and LG Medical Center. And then this authentication token also have the PQC-based digital signature algorithm, which is MN2. This is PQC application for medical center. The application consists of three parts, a database and its API. The API provide the PQC TLS session and service function of application. And then the service function of QPOP. QPOP is used for authentication and it has QRNG for key generation. Application UI is like that. When QPOP is inserted to PC, user can log in with typing password. And the PQC session is established, then the user can approach it to database. You can show the example of diagnosis images look like vessels in the eye. Industrial application is quite same with medical references. The difference is about policy of data. For example, medical data cannot be transferred from DB to the other storage in the Korea law, but just to look up it. Factory data would not be like that. In this year, we prepare new application service with PQC in culture industry. It is performance ticket reservation services. The service includes safe ticket reservation and audience management and ticket checking at the entrance. For this, we are developing PQC-based ticket app and POP USIM and PQC-based certification. Actually, POP USIM is already made and we are now developing authentication system. It is noteworthy that PQC services provide that through the 5G mobile network. Next service is facial recognition access system. There are many convenient access authentication systems. One of them is bioauthentication. Authentication methods such as fingerprinting and face have the advantage of being unique and convenient. I think that the security weak point of this system is section between facial recognition devices and the authentication server. A person's bio information cannot be changed. So therefore, this is one of the more secure information and PQC is used for this. This is our hybrid PQC algorithm in Korea for the government's secure equipment should be certified by trusted authorities. So PQC standard and PQC standard competition is now ongoing, and the verification criteria is not yet prepared. So the method combining verified key exchange, which is ECDH, with PQC was proposed. The key exchange is done twice using ECDH and our result. The final secret key is derived from the XOR of keys, which result of both key exchange algorithm. Note that this is a temporary way rather than improving security before establishing a complete PQC verification. We need to prepare in advance for the advent of quantum computers. And for LGU Plus, everyone's data is important and there is no service that does not require security. So LGU Plus pursue a universal quantum cryptography platform that protects daily life of our customers. Thank you for listening.
Thanks for the next talk. Before we move to the next talk, there is a short announcement. Some said they want to get the presentation materials, so maybe the chairs will post the presentation material on the homepage, and you can see that already the first talk, PQC transition and CPU, there is already posted the presentation slide. Next talk is on quantum security. The title is PQCrypto, the quantum security evaluation platform for cryptographic algorithms. Seokjun Lee of ETRI will give the talk.
Thank you, Mr. Chairman. I'm Seokjun Lee, principal researcher at ETRI, and we call it as E3, and want to introduce our PQCrypto platform. Quantum computing technology has been developing rapidly in the recent years. At this point, as cryptography researcher, we can ask the following questions. When will quantum computer break RSA crypto system, or how many qubits are necessary for the successful attack? Motivated by this concern, E3 aimed to evaluate quantum security considering the quantum environment and developed PQCrypto, the quantum security evaluation platform for cryptographic algorithms based on quantum resource estimation. So let me start this presentation. Quantum computer was proposed by Richard Feynman in the early 1980s. He points out that classical computers are not adequate for the simulation of quantum systems because there is no easy way to process a quantum state of many particles in the computer. So he proposed that computation would be much faster with a new kind of quantum computer. This was only a conceptual proposal, and it was unclear which advantage it could provide and whether it was technically feasible. However, David Deutsch proposed the first quantum algorithm showing exponential performance improvement in 1985. Peter Shor, inspired by Simon's result, created the famous Shor algorithm in 1994. This algorithm is known to be able to solve factoring and discrete logarithm problem in polynomial time and regarded as one of killer applications of quantum computer. Many companies have been interested in quantum computers since then. In 2011, John Preskill talked about quantum supremacy. Quantum supremacy means that quantum computers can solve the problems, but classical computer cannot solve it in feasible time. After that, people were wondering about which vendor or which company could be the first one to achieve quantum supremacy. The performance of quantum computers has been improved dramatically in recent years. Intel, Google, and IBM seem to take the lead for the number of qubits, but IonQ's quantum computer has good features that all qubits are connected and the gate accuracy is relatively high. Quantum annealing technology of D-Wave and photon-based method have more qubits, but they are not in the area of universal quantum computing. John Preskill, who made the term of quantum supremacy, said that the present is the age of NISQ. NISQ is the abbreviation for noisy intermediate scale quantum and refers to the era of noisy quantum computers with a reasonable number of 50 to 100 qubits. It would be more powerful than classical computer, but it may be difficult to obtain the correct answer due to the error rate. Google has made significant progress on quantum supremacy. According to the paper published in Nature in 2019, the researchers claimed to solve a hard problem in 200 seconds using Sycamore 54-qubit quantum processor. They argued that it would take 10,000 years with a supercomputer. The number of 10,000 years may be overstated, but even according to IBM's claim, it takes 2.5 days with a supercomputer. Although it is still the age of NISQ, quantum computers start to replace classical computers in some problems. Last year, IBM announced a milestone of building quantum computers with more than 1,000 physical qubits by 2023. Also, IonQ also announces the plan to build a quantum computer with more than 1,000 qubits by 2028. Simply looking at the numbers, you can feel that IonQ is quite slow compared to IBM. However, the number of qubits in the plan is not about physical qubit, but algorithm qubit in IonQ. So we'll talk about the difference between algorithm qubit and physical qubit after a few slides. Then let's go back to the first question. When will quantum computers break RSA? We already knew that Shor algorithm can theoretically attack RSA and ECC. So you can predict the time if you know the level of quantum hardware required by this algorithm. So how many qubits should a quantum computer have in order to break RSA or factoring? In this case of RSA 2048, which is currently widely used, our research has shown that quantum processor needs 4,098 qubits at least. Now, so look at that case in the NISQ era. To break it, the minimum number of qubits was 4,098 according to the table. Of course, there are currently no quantum computers with 4,098 qubits. Then, if a quantum computer with that qubit is developed, then will RSA 2048 be broken? The answer would be no. In order to bring quantum circuit at the algorithm level to a physical quantum processor, the following points should be considered. First, is it possible to implement arbitrary multi-qubit gate like Toffoli? Second, we have to consider the error rate of quantum gate. The current quantum processors usually have an error rate of 1% or more, which will decrease the accuracy of the entire circuit as it gets deeper. Third, how long will it take to maintain quantum coherence in the process? Fourth, is it possible to apply to qubit gate like CNOT to any random position of qubit? Some quantum processors allow CNOT to only to adjacent qubit. Considering these questions, we can say that the quantum circuit discussed at algorithm level cannot be directly applied to physical processor. So the quantum security should not be judged only by the number of algorithm qubit. Craig Giddens et al. Concluded that it takes 20 million qubits and 5 hours to factor 2048-bit RSA integer in their paper in 2019. To calculate this value, the paper assumed that physical gate error ratio is 1/1000, and the error correction code is surface code, and the physical processor is based on superconducting qubit. These values will vary depending on how physical qubits are implemented. Even for the same quantum algorithm, the required quantum resources will have different values depending on the hardware and the error correction code. In the light of Giddens' paper and analogy, the required physical quantum resource for an algorithm may vary depending on the performance of physical quantum processor and the type of error correction code. In any case, there is the research result of quantum resource in the physical layer about RSA with a certain assumption. Then, how about AS, ECC, secure hash, PQC, and so on? We are also interested in the exact quantum security of these cryptographic algorithms. What if we have a platform that provides a fast and automated way to evaluate the real quantum security for cryptographic algorithms based on precise quantum resource measurement? So we made PQCrypto platform. PQCrypto is a platform for evaluating the quantum security of cryptographic algorithms. It allows precise analysis of the required quantum resources to attack cryptographic algorithms. You can see our development environment of QCrypto in this slide. It works hard. It works on the web, and most of the core functions are executed on the server, so an installation is not required. On this screen, we can program the quantum circuit visually by inserting quantum library gate for arithmetic operation. The quantum circuit is translated to Python code, compiled to quantum assembly code, executed by quantum computing simulator, and analyzed for estimating physical quantum resources. The quantum computing process can be divided into the following levels: algorithm, QASM, quantum assembly QASM, FTQC, fault-tolerant quantum computing, and physical layer. Since the overhead for FTQC can be calculated by considering the physical quantum processor, QCrypto platform will analyze the logical resources and FTQC-based resources in the physical layer instead of applying FTQC only in QASM layer. Let me explain how QCrypto platform can help us figure out quantum security. Usually, in the quantum security analysis research and cryptography, we draw quantum circuit at the algorithm level. This quantum circuit is expressed in the form of a quantum reversible gate that performs a specific operation with logical qubit. This circuit on this slide is the multiplicative inversion in Galois field 2 to the 8, which is the most important arithmetic in AS S-box. This circuit may look simple, but internally it contains 4 multiplication of Galois field 2 to the 4, 2 multiplication inverses, and other logic gate. Logic gate for multiplication in Galois field 2 to the 4 can also be decomposed sequentially. It contains 3 multiplication in Galois field 2 to the 2 and 1 inverse operation. If you think of this as quantum programming, it's similar to the way we make a program code using library in high-level languages like C or Java on classical computers. If there is a way to insert quantum library as a logic gate in the quantum circuit, we will be able to make quantum implementation easier. What we need is a quantum library for cryptographic or arithmetic operations in the form of the visualized circuit implementation. Anyway, the full circuit in the algorithm level goes through the following process to measure the amount of quantum resources for each level. First, the drawn circuit is converted to a Python code automatically, and the code is compiled into quantum assembly code. If the number of qubits is less than 30, it is possible to verify the QASM code by executing it on a quantum computing simulator. And the QASM, quantum assembly, can be synthesized into a circuit suitable for the structure of the quantum processor and synthesized again to add quantum error correction code considering fidelity of quantum gate. We will have the resource analysis result in QASM level, quantum hardware-based logical level, and quantum hardware-based fault-tolerant quantum computing level. This slide shows the visual quantum programming for theoretical circuit. If you have quantum library for arithmetic used in the cryptographic algorithm, you can draw this type of circuit more easily. Visualized high-level circuit in the previous slide can be converted automatically to Python code. The first reason is that some people may prefer to program in Python code, and the second reason is that our compiler can translate Python code into quantum assembly code. Our platform can draw a quantum circuit again and calculate the amount of quantum resources at the QASM level. If you want to analyze the amount of quantum resources at the physical level, you can run the quantum resource analyzer of our platform. You can select some options for analysis. In this option, you can set the type of error correction code, the qubit layout in the quantum processor, circuit synthesize method, target fidelity of the full circuit, and the physical gate performance. By selecting these options, you can analyze detailed quantum resource at the quantum hardware logical level and fault-tolerant level. You can see a lot of information such as the number of qubit, number of each gate, gate depth, committing time, and so on. This is the summary of core features of PQCrypto. First, it provides a visualized high-level programming method for quantum computing. And second, it provides quantum libraries of arithmetic for various cryptographic algorithms. Third, it analyzed the amount of quantum resources in the QUASM, quantum hardware logical, and quantum hardware FQC level, respectively. There are still some points to be improved on our platform in short term. We are in the process of updating the manual supporting quantum circuit for large-scale qubit over than 1,000 qubit and various quantum libraries, and improving the accuracy of quantum resource analysis. In fact, we hope that our platform will draw this graph automatically soon. This is a long-term plan, but it will be possible to compare the quantum security of each cryptography or security according to each key parameter using this graph easily. So by PQCrypto, we expect to predict the time required for PQC transition if we analyze classical crypto algorithms and compare the result with quantum computer development trend. We also hope to compare the accurate security level of each PQC. For example, PQC A is stronger than PQC B in algorithm level, but PQC B can be stronger considering physical level of quantum processors. So we have plans to launch our platform in November 2021. We would like to operate it to be accessible only to the permitted IP addresses. So if you would like to use it, please send an email to me with your IP addresses. Of course, we welcome the researchers who wish to register cryptographic quantum libraries to our platform. Now, my presentation is over, but PQCrypto is just beginning. Thank you.
Thank you. I have a short question. You said you will open the PQCrypto in November, right?
Yes.
What is the how you share PQCrypto? For example, if I use the program, can I download it, or we can use in terms of cloud?
There's no download or installation, but you can access PQCrypto web page, and then you can use any our functions on the web server. So you only need to send mail to me with your IP address, because IP address is needed in the IP address should be in the list, permitted IP list.
Okay. There's one more question. Tanya Lange said, question for PQCrypto talk. How good are results compiled from Python compared to handwritten circuit? Is it optimized or what? I said.
Visualized circuit, visualized quantum programming is equal to the Python code. We can transit the visualized code to Python code. So they are level is equal. So
I think the question is your result from Python and compare with the handwritten circuit. It means optimized by human.
yeah.
So your result is good as human handwritten circuit, you mean?
In QGIM level, that will be almost same, but we go to physical layer, then I don't know, but how the result is. But anyway, we can analyze that.
If we compare the results, there should be a measure in terms of number of qubit or in terms of number of circuit. So you can answer the question in Slack channel later, I think.
Okay. Thank you.
Thank you for the nice presentation, and this is the end of this session. Thank you all.